Hello, everyone. We're excited to present the first international workshop on affective understanding in video at CVPR 2021 on Saturday, June 19. Videos allows us to capture and model the temporal nature of expressed affect, which is crucial in achieving human-level video understanding. Affective signals in videos are expressed over time across different modalities through music, scenery, camera angles, and movement, as well as with character tone, facial expression, and body language. Our workshop seeks to further explore this area and support researchers to compare models quantitatively at a large scale to improve the confidence, quality, and generalizability of the models. We encourage advances in datasets, models, and statistical techniques that leverage videos to improve our understanding of expressed affect, and applications of these models to fields such as social assistive robotics, video retrieval and creation, and assistive driving that have direct and clear benefits to humans.
We hope to cover the following topics: methods to recognize affective expressions evoked in viewers by videos, such as from music and audio, scenes, character interactions, and related topics. Methods to recognize affective expressions of people shown in videos, including facial expression, body expression, voice expression, and related topics. Ethics, bias, and fairness in modeling and data sets for the problem of affective understanding in videos. Multimodal techniques for understanding affective expressions, including non-visual signals such as audio or speech. Explainability and interpretability in the context of affective video understanding. Temporal context and scene context in affective video understanding. Cross-cultural analysis of affective and subjective annotations. Open public academic datasets to understand affective expressions in video. And finally, applications of affective understanding of videos to industry. Please see our website for an overview of our workshop. And because CVPR is virtual this year, our website includes links to watch all of our talks on demand and pointers to read all of the papers and details on our competition.
Our workshop is split into the following parts. From 10 to 12 p.m. Eastern Standard Time, we have a poster session facilitated by Gatherly, where participants can interact with paper authors and our competition winners. From 1 p.m. to 3 p.m. Eastern Standard Time, we will be streaming talks from our invited speakers. From 3 to 4 p.m. Eastern Standard Time, our invited speakers will conduct a panel discussion including prepared questions and those from the audience. From 7 to 8 p.m. Eastern Standard Time, we will have an introduction to our challenge and talks by the winning teams. And finally, from 8 to 9 p.m. Eastern Standard Time, the winning teams from our challenge will engage in a panel answering audience questions. Please submit your questions for both panel discussions using the following link. Thank you for attending the first international workshop on affective understanding in video at CVPR.
Okay, hello. Today I want to talk about an AI theory of mind. This is research that my students and myself have been working on for quite some time. And the idea is basically that in computer vision and machine learning, we have solved many problems like object recognition and face recognition. And by solved, I don't mean they're completely solved, but that there's been a lot of research done on them, and there are algorithms that are able to perform quite successfully in specific tasks. However, humans and specifically or other types of animals like apes are able to do much more complex tasks like the recognition of emotion, the recognition of intent, and the interest of others. And this is typically called in psychology and neuroscience theory of mind. So we just want to know how can we design computer vision machine learning algorithms that are moving us closer to that AI theory of mind. And part of this theory of mind is recognizing emotions and the intents of others, but also explaining the why that's sometimes called mentalizing, because we create a mental video of what occurs in specific cases, and we can then simulate specific conditions from specific agents. So to begin with, I'll start with emotions and then move into intent. Specifically for emotions, researchers in general agree that human emotions correspond to the execution of a number of computations that are executed by the central nervous system. So when there is an external stimuli, we respond to that, or rather the central nervous system responds to that. And there are certain outputs that we can observe. Some of these computations or outputs sometimes correspond to facial muscle articulations on the face. And these are called action units. That is a hypothesis that goes back to the Greek philosophers. Descartes also mentioned those, but it was really made famous by Duchenne, shown here on the right, and then by Charles Darwin a few years later. So the idea is that when we want to express happiness, most likely we want to do that voluntarily, or when we want to express surprise or fear, we move specific facial muscles on the face based on some basic concepts of how our central nervous system works and our culture of what we have acquired over time. So basically what is going on is that in our brain, we have an algorithm that creates these action units to specifically determine which of those emotion categories shown on the left, or which of these psychological variables, continuous variables shown on the right of your screen, arousal and valence, for example, actually correspond. So I want to emphasize, because this is not very well known in the CVPR community, that the brain does not encode emotion categories like on the left, or continuous variables like arousal and valence on the right, but rather we have a system of action unit recognition, which is biological motion recognition in the brain, that allows us to do recognition of motion categories and continuous variables like arousal and valence. If you are curious, we have a paper back in 2016 in Journal of Neuroscience. We actually show that this area that recognizes the action units is right here behind your right ear, in an area of the brain called the posterior superior temporal sulcus. So basically what happens is that then these action units that you have here represented as axes of a multidimensional face space correspond to either an active or inactive facial action, or action unit rather. And depending on which quadrant you are here, or in more dimensions, obviously there will be an octant, right? But basically in this quadrant, in this plot, when you are in this area, because you have this action unit active and this other action unit active, then you have a specific emotion category that is associated. In our culture, for example, it's associated to happiness. And then there's this other set of action units that are active or not active that is associated to the recognition of surprise. This is very interesting, and we have known this for many years, and we've published a number of papers about this that have been verified over and over again, both in the neuroscience domain and also used in computer vision and machine learning to design very successful algorithms, as I'll show. But a few years ago, around 2014, we were wondering what happens with these quadrants of the face space that we don't know what they correspond to, right? So like this one's empty areas here. If this quadrant corresponds to happiness and this one corresponds to surprise, what do these two represent? And the problem is that for these two, they have some action units that are active for happiness, but not all of them, and some action units that are active for surprise. So the hypothesis we had, could this be something like happily surprised because I'm expressing happiness and surprise at the same time? So we tested this in a large number of individuals in a large population in the US, and we actually found that this is actually true, that people generally perform this combination of action units to express things like happily surprised or sadly fearful. Most interestingly, as I said earlier, happily surprised has a combination of action units that comes from happiness and surprise. So for example, the action unit 12 and 25 are used here for happily surprised. Those come from happiness, and action units 1 and 2 come from the expression of surprise. Another, oh, by the way, this expressions here that are compound of two other emotions, we call them compound facial expressions of emotion, and you can read more about those in this PNAS paper in 2014. Another very interesting compound facial expression that we discovered back in 2016 is the nod face, and it's a combination of contempt, anger, and disgust. So meaning that it's a quadrant or an orthant of the space that has a combination of action units that correspond to these different other categories. And this is interesting because this expression, it's used to negate sentences. It's actually used in all the languages in the world that we have tested thus far to negate, and especially, but not uniquely, strongly negate some statements. And the importance of this is that this could be a hypothesis of how the evolution, or good hypothesis how language actually evolved through the expression of emotion. So as I promised, and most interesting for this workshop, we have integrated all this knowledge into a computer vision model that we published in the EmotionNet paper in CVPR back in 2016. And then basically, we just followed all the steps of these models, these cognitive neuroscience models that I have described, and built a system that can recognize these action units and then can recognize the categories of this basic and compound emotions. And basically, this allows us to recognize very accurately the action units with a combination of methods, including kernel subclass discriminanalysis. This is a method that we developed many years ago. And these are some of the results that you can get applied to video, where you just keep tracking of the movements of these facial muscles. So action unit 1 is the raising of the inner corner of the eyebrows. Action unit 12 is the pulling of the lips. Action unit 6 is the wrinkle of the eyes because of the raising cheeks, etc. IU 25, open mouth. So you see how this works. And this system is extremely robust, extremely simple to build with a certain number of convolutions and subclasses, and you're done. So moving on to newer stuff that we have been working on, I want to spend some time actually talking about other computations that are associated to the expression and recognition of emotion from others. So as I said earlier, researchers generally agree that human emotions correspond to the execution of a number of computations by the central nervous system. Our previous research, as that of many other people, have studied the hypothesis that these computations yield visually identifiable facial muscle movements. However, the expression of emotion, when I internally experience an emotion, I also corresponds to a number of, or an execution, of a number of computations that release hormones, or what's more generally known as peptides. Hormones is just a very specific type of peptides. So things like cortisol, testosterone, etc. What happens is that these peptides change not only the blood flow, but the blood composition. And most interestingly, the face is innervated with this huge number of blood vessels that are extremely close to the surface of the skin. Actually, if you look in the mirror very closely, you're actually going to see some of them popping out because they're that close to the skin. So the hypothesis that we had is that because when we internally experience emotion, we actually releasing a lot of peptides, that this blood flow and blood composition changes are actually visible on the surface of the face as a facial color change because of all these large number of blood vessels on the surface of the skin. So again, just to reiterate, the hypothesis here for happiness, surprise, and compound emotions like subtly fearful is not that you have a specific number of action units, active or not active, but rather that you have a unique set of colors that only occur in happiness, consistently occur in happiness, but do not occur in the other emotion categories. So to test this hypothesis and build computer vision systems that can do recognition of emotion from these facial color changes, we ran the following experiment, which you can find in PNAS as well, PNAS that we published in 2018. So basically, what we first did is we took a large number of faces expressing certain emotions, and we described them in what's called the isoluminant color space. For those of you that do not remember or do not know what an isoluminant color space, I'm going to do a very, very, very quick review here. So consider that we have a pixel, just one pixel, in RGB. So a pixel can be described as a vector of RG and V values, right? So this pixel describes both color and luminance. Luminance is what you see right here. So what defines the shading of the object, right? So you're very aware of shade from shading. For example, this is you use the luminance information of the object to extract the three-dimensional structure of the object. And that's thanks to the shading that is a function of the shape of the object and the position of the light with respect to the object. Isoluminant color are the two dimensions. Oh, I'm sorry. Just luminance is actually computed as a linear combination of RG and V, correct? So if you go into your favorite programming tool, you can just convert an image, a color image, into a grayscale. And what that function does, it just does a linear combination of RGB, right? So for example, we could just do C1R plus C2G plus C3B, right? And then, or just take a basic average of the three, if you will, and get an average luminance, and that's just the luminance variable. Now, the isoluminant color space, isoluminant means without luminance. So by definition, the other two dimensions of this three-dimensional vector actually define the color dimensions. And hence, color is two-dimensional, not three-dimensional, right? Color is just two-dimensional, at least isoluminant color is. So let me show you in a picture what this really means. So if I start with this face of this person here, and I first compute luminance, meaning I extract an average of the RGB values, this is the luminance variable that I obtain. Now, if I extract the two-dimensional orthogonal dimensions or the two-dimensional orthogonal, excuse me, to this luminance space, then I get the two color dimensions, right? And here are the two color dimensions. These dimensions tend to look really weird because we're not used to seeing that, but this is what we really mean by color, these two dimensions here. So if I now convert these three images to grayscale using the function that I alluded to, right? You can just convert these three images to grayscale. What's going to happen? Well, with the first one, nothing's going to happen. It's going to stay the same because it's already in grayscale. But these two are going to become completely blank. And why do they become blank? Because they don't have any luminance. The luminance on each pixel in that image is exactly the same. So hence, you don't see any shading in that image, right? The only information that these two channels carry is information of color. So what we want is to demonstrate that this color information, these two channels of just color, no luminance, no shading information, actually carry information of emotion. And what we did using computer vision algorithms that we've defined over the years, we detect the face, we detect a certain number of landmarks, a huge number of landmarks on the face, and we create this tessellation of areas on the face completely automatically. And then each of these areas, from each of these areas, we extract some statistics of these two color channels, right? So for example, you can compute the mean and the standard deviation, right, of each of the pixels in that region for this channel and then for this other channel, and that gives you a feature vector, the color feature vector that we can compute. And then we're just going to use a very simple linear approach, like linear discriminant analysis or something like that, right? In our case, it was LDA, but any simple linear method is fine, just to make sure that we don't overfit to the data to see whether these color statistics, again, just from color, no shading at all, can do recognition of emotion. And the answer is yes. And here's the p-value, 10 to the minus 50, which is beyond statistically significant. The answer is that just by looking at these color changes on the face, when the face fluctuates in color because of these peptides that our body's releasing because of the emotions that we're experiencing, that we can do this recognition. So basically, that computational model of what we have implemented in the brain that I was alluding to earlier not only has dimensions that correspond to the facial muscle articulations, but we have shown in this PNAS paper that it also has dimensions of color, right? So depending on which quadrant you are, depending on which colors, isoluminant colors you see on the image, you're actually interpreting an emotion or another, right? And we've all experienced this when people give us a really fake smile and we know it's fake, and it's because the colors, are not consistent with this. We're not conscious about this, with our brain is and actually knows how to recognize these things. So then a year later in 2019, we published this PAMI paper where we extended this to the recognition of, or we applied this rather to the recognition of action units. So basically what we did from these tessellations of the face that I've mentioned, we extract these color statistics, but in a functional way, right? So over time, over the video sequence, you extract color statistics for different channels of the color, and then you define templates of these functions that correspond to specific action units. And because the colors are going to correlate with the action units, because they are in theory correlated to one another, then you can do the recognition of the not only emotion categories, but also of the action units. And I'm going to spare you from all the details, but long story short, if you look at the results, when you combine in this paper the results of action unit classification based on the methods that I was alluding to early on from EmotionEd, where we only use convolutions on the image, on the shading of the image, and now you combine this with the color channels that I have described here, then the recognition, the accuracy, and the F1 score, this is actually F1 score, actually improves significantly. So the next thing I wanted to talk about to complicate things a little bit more is the biological motion. So I've talked about facial biological motion, the action units. I have talked about the color on the face, but now I want to go to the body, and I'm going to treat first the body just as a single entity, just like a dot, right? And my interest is to know whether something occurs because there's an agent that's behaving intentionally or an agent that's behaving non-intentionally. Maybe it's just mechanical motion. So let me show you two videos. I want you to pay close attention to these two videos and determine whether the agent in that video is doing an intention, or whether I have an agent in the video or not, rather, right? If I have an animate object that's just moving because there's mechanical motion, or if there's actually an agent that's behaving. So here you see there's a ball and there's a platform that rotates, and the platform is just pushing the ball around. So there is no intent, it's just pure mechanical motion. There is no agent performing any specific task. And now let me show you this other example. Here, as you can see, now all of a sudden, there is an agent who is actually acting intentionally. And the intent is to precisely avoid the platform, to be hit by the platform, right? And why can we do that recognition? Well, we humans can do that recognition very simply because we have a knowledge that we have acquired, which is that the total amount of energy in a closed system can never change, right? So I can have mechanical energy, I can have kinetic energy, but the sum of the two, one can be transforming to the other, but the sum of the two has to stay constant. There's no ways I can add energy into that system. However, when I have a motion like this, right, an intentional action, there appears to be an increase on the total energy. And that's because there's a non-observable chemical energy stored in that agent that is being burned somehow to actually perform this task, like jumping or moving around. Well, this is non-observable, so there is an appearance that the amount of energy that is being generated, or total amount of energy that is in that system, is actually increasing, right? So we've designed computer vision algorithms, machine learning algorithms, to actually detect that there is an increase in total amount of energy. This was just published this year in IJCV. And you don't need even any training data, right? You can just do unsupervised visual recognition of intentional actions like this. So the reason this is pretty cool is because now we can apply it to real videos like this, right? So I'm going to show you a couple videos, and one has an intentional action only. The other one has a non-intentional action. So let's look at the first one. Here goes the first video. It's a guy shooting a ball goes in, another guy running, nothing is special. Everything is intentional in that video. But how about the second one? This, if you remember the ice bucket challenge a few years ago, this guy is going to, whoops, okay. So you can very easily detect when there is an action that is performed by the guy behind the with the blue t-shirt, right? That's actually performing a task that is non-intentional, very clearly. Well, we can apply this algorithm that I just described to actually detect when these things happen, right? And in the IJCV paper, we have a number of examples where we show people like what I just shown, or a person is skating, and at which point, shown here in red, right, the person actually is performing an action non-intentionally, right? So now we can detect the intent and non-intent from these different videos, from these different components of the video. So going back to my computational model that I keep modifying, right? For emotions, we've shown that we have action unit recognition, which is biological motion on the face. We also have color changes on the face, which are important. And I've now shown that there are actions that, or specific properties of the action that I can extract using computer vision that detects the intent of that action. There is one more context. I don't have time to cover it here, unfortunately, because the time that I'm given, but you can also look at the paper I published, a short paper in PNAS in 2019, where I detail these things a little bit further. So the last thing I wanted to mention very briefly is mentalizing. And I said from the very beginning that part of theory of mind is actually mentalizing, the ability for me to run internal movies of what might have happened or what may happen. And this is a pretty important task that we humans perform and computers are still not able to do. So here's a paper back from 2018 in ECCB called Ganimation, where we actually show that given a face, this is just the first row, it's the face, the same face repeated over and over and over again, that given that face, we can actually design generative models that can edit the action units, right, the AUs that I've mentioned at the very beginning of this talk, to simulate that action unit 1 is active, right? So this is not active in the beginning, and then you can see here action unit 1, the inner corner razor of the brows, that eyebrows are going up, up to the maximum. The outer brow corner razor, AU2, AU12, which is the classical smile, right? The pulling of the lips, AU25, which is mouth open, and so on. So now I can do simulations. This is a real image, and all these are fake images or synthetic images that I've generated by applying this algorithm, where I can actually apply, say, action unit 12 and 25 to create this, classical open mouth smile. More recently, we have actually designed another method which represents this action units. Well, this was the same here. These action units are represented in some latent space, but now we're going to represent actions that are more complex into latent space, like intent and non-intent that I showed from these videos with the balls moving, right? Either intentionally or non-intentionally. So I have a generative theory of my model now that from a latent space is able to simulate some action, some video of an action, right? And my generator is able to generate the environment and the action itself to generate what would be intentional actions or what would be non-intentional actions here. So let me show you some examples of how this model, or what some examples of what this model generates. So these are some mentalizations of the model of intent. So this is what the model has learned to generate that it considers to be intentional actions. So this is an intentional action, or the model considers this to be something that can only be done intentionally. This is the second one, and a third one, and two more. So this is my fourth example. And you can see they're all clearly intentional actions, right? Only an agent would be able to perform that. And I'll compare this with what the model considers to be a non-intentional action. So this is number one. As you can see, just a ball falling and rolling. Number two, again, just moving mechanically with absolutely no intent. Number three, same thing, just bouncing around. And number four, just bouncing on walls, moving according to the motion, the Newtonian physics that we all have learned. We are also extending this to the recognition of intent and non-intent in videos. So one ability that we humans have is that you can actually, when we observe an action, we can actually internally run that movie and determine, is that an action that I can perform intentionally or not, especially for complex actions, right, or tasks. So we can do that. We observe a video, and then from that video, what we do is we recover the latent variable representation that's closest to that video, and then we regenerate the video, and then we see whether that video that we regenerate with the model of intent actually fits the original video better than the model generated down here from non-intentional actions, right? And then that is going to allow us to determine whether it makes sense for this to fit into an intentional, non-intentional model. But other than that, we can extend this also to, or we are extending this to to the generation of other videos that are more complex, not just balls moving around. Here are some examples with human bodies that we are applying this to. So I've shown you that we can apply some of these things to the face to generate facial expressions, moving specific action units. Here is for the other articulations in the body. So this is actions that the model considers to be done intentionally, just walking around, fighting, dancing, and maybe petting a dog or an animal. And this to be compared with actions that are performed by the model that are non-intentional. So things like falling forward, just tripping, falling down, and falling backwards. All right, with this, I'm just gonna close it for today. I really appreciate your time. If you have any questions, I'm here at the conference, so don't hesitate to contact me. I'm happy to discuss these things further. I want to thank my students. It's a privilege to be here talking about these projects, but as you know, this work was not done by me, it was mostly done by my students. So I want to acknowledge them. Here are most of them, and here are some of the past students that have also worked on these projects. And I want to give special thanks also to our funders, especially NIH, who's been funding us for years now, and also some funding that we've gotten from the HFSP, NSF, and NBI. Thanks.
Thank you for the invitation to present at this CVPR workshop. My name is Daniel McDuff. I'm a principal researcher at Microsoft. And today I'll be presenting about our work building computer vision tools for recognizing cues associated with both internal and external expression of affect. the types of applications that we're most interested in revolve around health and well-being. And it should hopefully become obvious how some of the things that I'll present could be applied in contexts of applications such as telehealth, ubiquitous health and well-being measurements such as fitness applications, but also more broadly in applications such as gaming and also productivity. I'll focus primarily in this presentation on the sensing aspects of our work, aiming at creating ubiquitous health and well-being sensing platforms for everyday devices. And in particular, we're doing a lot of work to optimize these to run on device to create applications that preserve privacy and also improve user experience. The types of signals I'll be talking about are primarily physiological and facial, and these include measuring cardiac signals like heart rate and heart rate variability, pulmonary signals like breathing and respiration, and facial actions. In terms of the vital signs that we're interested in, as I mentioned, these are primarily cardiopulmonary signals, as these can be measured through computer vision tools. We've already done work looking at measuring pulse or heart rate variability, respiration, blood oxygenation, and also there's some interesting work looking at detecting things like arrhythmias and other abnormalities in the pulsatile waveform. Going forward, there's compelling and exciting work looking at ways that we can measure blood pressure or correlates of blood pressure using some of these techniques. And as imaging hardware develops and we get new forms of cameras that can measure beyond perhaps the RGB spectrum, then there's the hope to capture additional pieces of information, such as perhaps body temperature, and then maybe some of information about the composition of the blood through glucose, etc. But to give you context, here's an example video showing two subjects where we're analyzing the RGB video, and you can see the pulsatile waveforms captured via a contact sensor and via the camera. In this second example here, you see two other videos where the input is captured via near-infrared camera. In both cases, you can see that the camera-based measurement can get pretty high alignment, particularly in the RGB space with the contact sensor, even in the presence of facial expressions and head motions. So we can, in a contactless way, just using a regular RGB camera, we can capture these signals. And near infrared is a little more noisy. In this case, the models were trained on RGB data and then tested on near infrared videos. But this provides the possibility of measuring in low light conditions, such as for a baby monitor or driving scenarios. In addition to measuring physiological signals, I'll also be talking about measuring more external expressions of affect. And typically for this, we use facial action units as a taxonomy for describing the displays expressed on the face. In addition to tracking facial action units, typically we'll look at head motions and other types of behaviors in order to quantify overall activity levels and things like that. One of the things I want to focus on a lot in this presentation is how we're using synthetic data to train these systems. In the past, we relied entirely on video data sets, which were time-consuming to collect, involved bringing people to a lab, recording videos of them under various conditions, and in the case of training physiological measurement systems, involved collecting ground truth physiology via contact devices. And this, again, this is very time consuming. It requires a lot of cost and effort. Moving forward, we are moving to use a lot more synthetic data where we render avatars using graphics tools to create data that is high fidelity but we can also control many of the parameters, such as the background conditions, the lighting, head motion, facial expressions, as well as superimposing physiological changes driven by real pulsatile and respiration waveforms. To give you an example of what that pipeline looks like, when constructing these avatars, for each frame, we augment the base color and subsurface scattering parameters for the skin texture on the avatar using information about the pulse or respiration signal. And then we also control the motion, particularly of the torso of the avatar, using respiration information to capture motion due to breathing. We can then also drive the avatar using information about head pose or facial actions that we want them to exhibit in these videos, and augment different background or lighting conditions. And this allows us to create many videos very scalably. The nice thing about synthetics is that it also gives us a lot of additional information. So we not only get the RGB videos of these avatars, but we also get high fidelity ground truth about things like depth, segmentation, landmarks, surface normals, etc. And then using this pipeline, we can create many thousands of videos of avatars under different conditions. Of course, with this high fidelity ground truth, not just in terms of depth and segmentation, but also the physiological changes that we used to drive their creation. And these can be used as training data sets. Typically, the models that we're training from a computer vision perspective are based on optical principles. When looking at measuring physiology from video, typically what we're trying to do is recover subtle changes in light reflected from the body due to the physiological processes, and separate these from other types of changes in pixel intensity due to head motion or ambient lighting changes. In doing so, we really want to capture the changes in diffuse reflection, which are typically contain the strongest, for instance, pulsatile waveform. One such model that we've created to do this is the multitask temporal shift attention network. So this model takes as input a series of frames, and we help the network to recover subtle changes in pixel intensity associated with the physiological information by giving it as one input a motion representation, which is essentially the difference of two successive frames. You can think of this as almost as an optical flow type of representation. And then a separate appearance branch which takes as input the current frame of video. And this appearance branch helps drive an attention mechanism so that the motion branch can focus on the relevant regions of the image corresponding to, for instance, skin, which we know, of course, will have a higher pulsatile information than clothing or other regions of the video. One important thing to note about this network is that we typically train it with the derivative of the pulse or respiration waveform. Because we're providing as input this motion representation, and we find this is particularly successful at helping us learn the physiological changes from the video. Another innovation here is to leverage temporal shift modules in order to reduce the computational load of this network. So we could use 3D convolutions here to capture temporal and spatial information, but that can be very computationally expensive. And when our goal is to run these algorithms on device, it's not very practical. The temporal shift modules do a really good job at capturing some of this temporal information alongside the spatial information, while really reducing the overhead in terms of computation. In terms of synthetics, we've tried several different ways of training our networks. One is to combine synthetic data with real video data in our training sets, train our network, and then test, of course, on real video data sets. This tends to be the most successful. Training only on synthetic data still leads to a sim-to-real gap that we're working on addressing. But when we combine real video and synthetic video together in the training set, we typically get results that outperform just using real videos. And as we increase the number of avatars that we synthesize and scale that, we see fairly consistent improvements in terms of reduction of heart rate estimation error and improvements in signal-to-noise ratio of the underlying waveforms. So Synthetics pipeline gives us this way to continually generate more and more data and improve the robustness of our algorithms. Of course, there is some saturation point. As you can see in these graphs, you get diminishing returns with larger and larger numbers. But as the synthetics pipeline becomes more robust and developed, I think we'll see that we can push these numbers down or up with larger and larger numbers of synthetic data. We have a couple of open source toolbox, one in MATLAB and one in Python, that you may be interested to look at if you're starting out in this space as a way to get familiar with some of the existing methods. In terms of results, here's a comparison of heart rate mean absolute error across one of our video data sets for different methods, starting from our early methods using unsupervised signal processing techniques, which is represented by ICA here, all the way through to our latest work, which was presented at NeurIPS last year. And you can see we've been able to reduce heart rate error from close to 6 beats per minute error to under 2 beats per minute error across this relatively large data set. And this is thanks to including, for instance, the temporal shift modules, as well as using things like synthetic data and being able to train in multitask manner. In terms of respiration, we see similar improvements, a little less dramatic. Respiration measurement is slightly harder, or it's easier to do with more basic methods and harder to get improvements with more complex methods, just because the motion signal typically is slower than the pulse signal, and that makes measuring it accurately over shorter time windows just more challenging, particularly from a frequency estimation perspective. We've worked hard to reduce the latency of these models while maintaining the performance in terms of accuracy or error. And you can see the multitask temporal shift convolutional attention network highlighted in yellow really provides a nice trade-off. And we can get that running close to 150 frames per second while maintaining pretty low error rates. One thing we're doing now with these models is to create apps using them that we can deploy longitudinally to start to look at how non-contact measurement could be used for understanding health and well-being. So you can imagine this as a fitness tracker or well-being tracker for your laptop or for a device that has a camera. And we're measuring pulse, respiration, HRV information using these vision techniques, and then also combining that with information about facial expressions. And then participants that opt in can then track this data on their machine longitudinally to look at affective diurnal patterns. And I'll show some examples of those later. The longitudinal deployment typically involves people installing this software at their workstation. And again, it's privacy preserving in the sense that we can compute these things locally. But they can also be streamed to the cloud for sort of further or more aggregated analyses if that's something that we need to do as part, for instance, of a research study. One thing that we've found is pretty strong evidence of diurnal patterns, both in terms of expressed affect, but also physiological changes. So what you can see in this slide is a few graphs showing the average day for a number of participants who've opted into our studies. You can see in the top left-hand corner the average number of hours in which we detected a face in front of their workstation. So that's just showing kind of the rhythm of the day for most people. This was pre-COVID, so they're coming into the office. They tend to be in front of their workstation in the morning, then they may leave around lunchtime, and then come back in the afternoon, and then typically leave the office around 5 p.m. Looking at facial expressions, we see peaks in positive affect in the morning and the afternoon, and a dip in the middle of the day. And this is likely to be due to essentially energy levels. So as people have lower sugar levels, they're less likely to express positive affect. After lunch, they get a boost in energy, and that's likely to increase expressions of positive affect. Negative affect shows a much more sort of linear increase or monotonic increase across the course of the day. And we think that this might be due to just increases in tiredness and again, energy dropping across the course of the day, meaning people are more likely to express negative affect, frustration, things like that. In terms of physiological signals, we see diurnal patterns in heart rate that are very consistent with prior work, that heart rate tends to be lowest at the beginning of the day, peaks right in the middle of the day, and then drops again towards the end of the day. What's interesting is that these diurnal patterns are quite highly correlated with things like cortisol levels. And so you can see here an example from prior work where the same diurnal pattern in heart rate, where heart rate is lowest when you wake up in the morning and then highest towards the middle of the day around 1 or 2 p.m. And this is in part due to cortisol levels dropping throughout the day. And so we're really interested in seeing if we can detect essentially disruptions in these diurnal patterns. One thing we're trying to push forward is not just relying only on things like measuring average heart rate, average respiration rate, but also looking at other types of physiological information that we can capture via cameras, which we can't often do using contact sensors because they only have point measurement. And what you can see here is examples of magnified videos where we're magnifying on the left-hand side the pulse information. And as you can see from a video, what that means we can do is we can capture spatial information about the pulse blood flow. And peripheral hemodynamics capture a lot of information about stress. And we've been finding that these parameters that we can capture, including things like vasomotion, are often more robust indicators of stress than, for instance, changes in HRV, or at least are easier to detect via the camera. What you see here is changes in peripheral blood flow across time for an individual before some kind of stressful stimulation, during that stimulation, and afterwards. And you can see that the variability in peripheral blood flow tends to decrease during periods of stress. And also the pulse waveform. So these peaks here you see in the bottom plots are the pulse peaks. The amplitude of those also tends to pinch during these periods. And so you can see we see reductions essentially in power in those frequency ranges during stimulation. And we've found that, yeah, by measuring these signals like vasomotion and peripheral pulse amplitude, we're able to detect changes in physiology during periods of stress compared to periods of rest, and that these changes tend to be more significant than changes in HRV. And HRV is notoriously difficult to measure because it requires pretty precise information about pulse peak timing, whereas these peripheral pulse measures just require knowing the power of the waveform in certain frequency bands, which we tend to find is less susceptible to corruption from other types of noise that might be present. In order to personalize these algorithms, one thing we're using is meta-learning. And this is some really interesting work in collaboration with Xin Lu at the University of Washington, where we're using mobile devices to capture small amounts of data from individuals in order to customize a model and personalize it to them. And we can do this both in an unsupervised manner, where we use maybe post predictions from an existing model, or in a supervised manner where we collect ground truth data from those individuals in order to customize the model. And we have found that meta-learning, both unsupervised and supervised, tend to have a fairly substantial impact on the accuracy of the model, and in particular help make these models more robust to skin type, which is something that is a particular challenge in optical measurement because of the ways that cameras are designed and things like that. So by personalizing these models, we're able to reduce the error, particularly on darker skin types, quite significantly. While we don't have perfectly equitable performance here, that's something that we can push towards. So that brings me to the end of my presentation. As I mentioned at the beginning, the types of applications that we're building towards are thinking about ways that this technology can be used in contexts such as telehealth and fitness and well-being. But there are more applications that could be developed beyond that. You could imagine how some of these measurement tools could be used to make computer games more adaptive and engaging, and also potentially used in productivity scenarios as well. There's a long way to go in the non-contact physiological measurement domain, but it's a very exciting area where there's a lot of potential, both to increase the accuracy by which we can measure these signals, but also the types of signals that we can measure. As I mentioned at the beginning, we're really trying to move beyond just pulse and respiration measurement, and think about ways that we can get reliable information about, for instance, blood pressure. And this might be done through capturing pulse timing. So from different parts of the body, we would be measuring pulse transit time, or looking at pulse waveform morphology, or some combination of the two. We have a few resources that are available, including a blog post which kind of summarizes some of these concepts at a high level, particularly thinking about applications in telehealth. Some of our recent publications are highlighted there, and also those GitHub repos that contain MATLAB implementations of some of the earlier signal processing methods, which use typically ICA, PCA, and other types of source signal separation to capture physiological information from video, and also the later deep learning techniques, including the MTTS CAN model, which is implemented in Python.
Hi everyone, I'm Chujun Lin. I'm a postdoc at the Department of Psychology and Brain Science at Dartmouth College. Today, I will talk about our new work with Mark Thornton on how people infer others' mental states and traits. Here by mental states, we refer to a person's momentary states of the mind, such as emotions and thoughts. Traits refer to more enduring characteristics of a person, such as whether someone is young, extroverted, or trustworthy. We will show you evidence on how mental state and trait inferences are causally linked. I will first walk you through the motivation of this work, and then present 4 studies. All studies are pre-registered on Open Science Framework. You can access the data and codes via this link. Our preprint will be coming soon. First, why are we interested in mental state and trait inferences? Because they are both independently important for understanding human behaviors. Here, I'm going to show you an example that illustrates why understanding others' mental states is important.
Let's see. It's a boy!
The boy.
Yes!
Now, you might not even be explicitly thinking about it, but our brain has already filled in the gaps. Why did the little girl suddenly start screaming, crying, and jump to the ground? She was probably feeling very sad and disappointed. But why? Well, she probably does not want a baby brother. Let's see whether that is the case.
Tracy wanted a girl, obviously.
Our guess is not bad. This example shows why inferring mental states is an important tool for us to understand other people's behavior. Here is an example about why understanding others' traits is also important. If we know that a coworker is a serious person who does not laugh that much, we will likely not attempt to tell a joke in the next meeting with this coworker. That is, understanding our coworkers' traits saves us an awkward moment of them not laughing at our jokes. These 2 important human cognitive processes of inferring mental states and traits have also inspired AI research, like in the domains of human-robot interactions and multi-agent systems. For example, in this very interesting paper by Robin Novus and colleagues, they proposed a machine theory of mind network, in which an agent learns to understand other agents. In this network, there are 3 important components. The character net, which learns the general types of the other agents. This is like humans learning about other humans' personality types. The mental state net, which learns agent-specific mental states online. This resembles human inferring the mental states of other people given the situation. Based on the character net and mental state net, this agent predicts the subsequent behavior of other agents. This resembles how humans predict others' behavior by understanding their mental states and traits. So why are we interested in the relation between mental state and trait inferences? Because the connection between them is likely to have important real-world implications. For example, when judges evaluate the legal responsibility of a defendant, it is critical to infer the defendant's mental state at the time of committing the act. On the other hand, people form trait impressions of others based on superficial cues, such as their faces. We are likely to think that someone is trustworthy simply because their face looks more trustworthy. If inferences of mental state are affected by inferences of traits, then legal decisions might be biased by how the defendant's face looks, which recent studies seem to suggest that is the case. This example shows why understanding the connection between mental state and trait inferences is important. Indeed, recent research suggests such a connection. For example, in one neuroimaging study, researchers obtained the brain activity patterns when participants thought about famous people. They also obtained brain activity patterns when another group of participants thought about various mental states. In addition, they asked another group of participants to rate how often they think these different famous people would feel each of the mental states. With this data, they computed the weighted sum of the mental state patterns by the mental state frequency for each famous person. They tried to predict the brain activity patterns when participants were thinking about how these famous people are like in general. With this weighted sum mental state brain activity patterns, they found that matched target patterns provided much better predictions than unmatched target patterns. These findings suggest that mental state and trait inferences are indeed connected. In particular, the brain represents others' traits as the weighted sum of their mental states by frequency. Given those promising findings, here comes the questions we want to address in the current work. Existing research that suggests there is a correlation between mental state and trait inferences all relied on quite artificial contexts, such as asking about famous people who participants do recognize, but probably do not know much about, or using static face as stimuli, while in real life, we see people move around in their natural surroundings. Therefore, first, we want to understand, does the correlation between mental state and trait inferences generalize to more naturalistic contexts? Study 1 and Study 2 address this question. Furthermore, it remains unknown whether there is a causal relationship between the two types of inferences. That is, does one type of inferences causally shape the other? Study 3 and Study 4 address this question. Okay, let's jump right into the first study. In this study, participants will show video clips and evaluate a given target in the clip. The videos are from a previous study by Chen and Whitney. All videos are colored and muted. They range from 30 seconds to 3 minutes. They include Hollywood movies, home videos, and documentaries. They also varied in the number of characters, ranging from 1 to multiple. We analyzed the mental state ratings and trait ratings given to the characters in these videos. The mental state ratings were obtained from Chen and Whitney's. Their participants viewed the videos and gave continuous ratings to the targets on valence and arousal. Valence describes how positive or negative the emotion is, and arousal describes how intense the emotion is. Valence and arousal are key dimensions that describe various mental states. Here is an example of the rating data for the video clips shown in the last slide across time and participants. Now we can condense this time series data into frequency data. We plot each pair of valence arousal rating for a given time point by a given participant into this two-dimensional valence arousal space. And we can do so for all time points and all participants in the time series, by which we end up with a frequency map that shows how frequently this target was given a certain valence arousal rating in this space. The brighter color indicates higher frequency. As I mentioned, valence and arousal are two key dimensions that describe various mental states. However, in everyday life, We don't just go around and say, oh, this person is feeling high valence, or that person is feeling low arousal. Instead, more often, we describe mental states using discrete labels available in our language, such as this person is feeling happy, that person is feeling sleepy. So we try to match the frequency of all the points in the two-dimensional valence arousal space to the frequency of meaningful discrete mental states. To do so, we projected a comprehensive set of 60 mental states that we have words for to the same valence arousal space. This projection was based on online participants' ratings about how each mental state could be described by the dimensions of valence and arousal. These ratings were from a period study by Tamiya and colleagues. Then for each continual point in the space, such as this red dot, we can match it to its nearest discrete name mental state, in this case, dominance. If we do so for all the points in the space, we will end up with such a nearest neighborhood partitions, where the color indicates how often a valence arousal rating given to the target in the video falls within that partition. Again, the brighter color indicates higher frequency. By doing so, we can represent each target as a vector of mental state frequency across the 16 mental states. For example, this is the police officer we saw from the video in the previous slide. And here is his frequency vector based on the ratings he received from the participants. And this is another target and a frequency vector. Using these vectors, we can compute how similar each pair of targets are. Next, we collected the trait ratings of the targets in the videos. Specifically, our participants were first told which one of the characters in the video is a target they are supposed to keep track of. This was indicated in a static frame from the beginning of the video where the target was first seen. Then before viewing the video, participants were asked to rate this target on different traits based on the first impression. Then they view the videos and rate the targets on those traits again after viewing the videos. At the end, we double-check that participants remembered which was the target they were asked to keep track of. With these trait ratings, we can also compute the similarity between each pair of targets. Now to draw conclusions about whether mental state inferences and trait inferences are correlated, we can compare the similarity among the targets based on the mental state ratings and the similarity among the targets based on the trait ratings. We found that mental state frequency similarities and post-video trait similarities were correlated. This result indicates that people make associated mental state and trait inferences when judging targets in naturalistic stimuli. Interestingly, we expected that after viewing the video, participants should update their first trait impressions about the target according to the target's mental state they observed in the video. That is, mental state frequency similarities should be more correlated with post-video trait ratings than pre-video trait ratings. However, what we found was that mental state frequency similarities and pre-video trait similarities were also correlated, and to a similar extent as the post-video trait ratings. These findings suggest a directional relation between mental state and trait inferences. In particular, the trait impressions formed based on that static frame at the beginning of the video might influence mental state inferences throughout the video, but observing the target's actual mental states does not seem to lead to corresponding update in the trait inferences. However, we know that this finding provides only weak evidence of causation, which we investigate further in Study 3 and Study 4. To sum up, Study 1 shows that mental state frequency and trait inferences are linked in naturalistic context. However, it remains unknown whether this link generalizes to targets who are personally relevant, like our families and friends. Study 2 addresses this question. In this study, we asked each participant to name 10 people who they are personally familiar with. Then we ask participants to rate these familiar people on mental state frequencies and traits. For mental state frequencies, we have selected a list of mental states, like contemplating, shown here. We ask, how often is this person contemplating? That is, how often is this person thinking deeply and carefully? The participants rate the frequency on a 7-point scale for each familiar person. Based on these ratings, we can compute for each participant how similar their 10 familiar people are in terms of mental state frequencies. For traits, we have selected a list of traits, like extroverted shown here. We provided a statement. This is an extroverted person. That is, this person is outgoing, talkative, and sociable in general. And we asked participants to rate how well this statement describes each familiar person using a 7-point scale. Based on these ratings, we can compute for each participant how similar their 10 familiar people are in terms of traits. As what we did in the first study, we compared the familiar people similarity computed based on mental state frequencies to the familiar people similarity computed based on traits for each participant. We found that mental state frequency similarities and trait similarities were correlated. This finding indicates that people make associated mental state frequency and trait inferences when judging personally familiar targets in real life. To sum up, Study 1 and Study 2 show that inferences of mental state frequencies and traits are reliably associated in naturalistic and practically relevant contexts. Next, we turn to the causality question. Does making two targets appear to have different traits cause people to infer that they will experience more different mental states across a range of situations? Does making two targets appear to experience different mental states across a range of situations cause people to infer that they will have more different traits? Study 3 and Study 4 address these two questions respectively. In Study 3, we manipulate the target's traits and observe how participants make mental state inferences about the targets. To manipulate the target's traits, we use a short biography. We focus on manipulating the warmth and competence of the targets here, because they are two key psychological dimensions that describe how our perception of people are. In the biography, we have a short text that describes the target's warmth and competence. We also show a face that matches the text description. For example, this target is manipulated to have high warmth and high competence. So we selected a face that receives the highest warmth and competence ratings from a much larger face database. Here is an example of a different target who is manipulated to have low warmth and competence. Each participant views one target biography, and then the participants were asked to evaluate the target's mental state across different situations. For example, in this situation, imagine Mary is in an elevator. Which of the following mental state is Mary more likely to be in? In all situations, participants were provided with this same set of 6 mental states as options. These 6 mental state options were representatively sampled from a much larger set of mental states. For the selections of situations, we make sure that when there is no effect of the trait manipulation, none of the 6 mental states should be selected more often than the other across these situations. Based on the participants' choices across a range of situations, we can compute how often each mental state was selected for each target. And then we can compare whether the more different the targets were manipulated to be in terms of their traits will lead to more different inferences of mental state frequencies. Indeed, we found that the more dissimilar the traits that the targets were manipulated to have, the more dissimilar the inferences of mental state frequency they elicited. This finding indicates that manipulating inferences of traits causally shapes inferences of mental state frequencies. Next, we investigate the other causal direction. We manipulate the target's mental state frequencies and observed how participants infer the target's traits. To manipulate mental state frequencies, we use a statistical learning paradigm. Each participant was first told the name of the target they were going to learn about. There is no face used in this study. Then participants were shown a series of situations. For example, in this situation, imagine Olivia is with an annoying acquaintance. Then participants were asked which mental state is the target more likely to feel, tiredness or rage. Each situation is matched with a different set of 2 mental state options. These 2 mental state options were selected based on online participants' ratings, so that both mental state options were rated most likely to be elicited by the given situation. After participants indicate their answers, they will be provided with feedback whether their answer was right or wrong. For example, if I answer rage here, I will be told that Olivia actually experienced tiredness. This correct answer is designed to manipulate the target's mental state frequency, because across a series of different situations, we can calculate the frequency of the correct mental states that the target experienced. We design different correct answers for different targets so that their mental state frequencies are maximally different from each other. After learning the target's mental states across a range of situations, the participants were asked to evaluate the targets on a series of traits. For example, this is a question about the trait extroversion. Participants provided their ratings on a 7-point scale. Using these trait ratings for each target, we can compare how similar each pair of targets are. Finally, we can compare whether the more different the targets were manipulated to experience different mental states, the more different trait ratings they elicited. We found that, indeed, the more dissimilar the mental state frequencies that the targets were manipulated to experience, the more dissimilar the inferences of traits they elicited. These findings indicate that manipulating inferences of mental state frequencies causally shapes inferences of traits. To sum up this talk, I have presented you 4 studies that show that inferences of mental states and traits are not independent. Humans link these 2 forms of social informations to gain deeper insights of other people. Inferences of a target's traits causally shape how people infer the target's mental states across a range of situations. And inferences of a target's mental states across a range of situations causally shape how people infer the target's enduring traits. We hope that integrating this bidirectional causal relationship between mental state and trait inferences in AI design would enable a more flexible machine theory of mind. To end this talk, I would like to give a big shout out to my postdoc advisor, Mark Thornton. I've learned a lot of new skills and new ways of thinking during this collaboration. I would like to thank Diana Tarmia for sharing study materials, my labmates Landry Booth and Lindsay Tupfer for their helpful input. I would like to thank my PhD advisor, Ralph Adolphs, and labmates Umi Callis and Dora Clayman for their constant support. Finally, thank you all for participating in this talk.
Hi everybody, thanks so much for coming. My name is Alan Cowan and I'm currently the Chief Scientist and CEO of a private lab and scientific consortium called HumAI. I was previously a visiting faculty researcher at Google and a postdoc at UC Berkeley. About 6 years ago, I set out to develop new ways of modeling emotional behavior using computational methods. And I think those methods have really opened up exciting possibilities for understanding the role of emotion in our everyday lives. And so today I'm going to introduce you to those possibilities and attempt to give you a new perspective on emotional behavior and how we can train AI that understands it. So let me start by giving you my 2 cents on why computers might need to understand human emotion. And this is because I think it informs this problem of why we would want to understand emotions in video and how we would go about doing that. And so it goes back to David Hume's argument that reason is and only ought to be the slave of the passions. And the crux of that argument is that if you want to know what makes us tick, why we get out of bed in the morning, why we think about anything, why we do anything, you're eventually going to have to understand the emotions, why we feel things. In other words, emotions are the things that you're ultimately going to reference when your kid asks you why over and over, like why you're going to work and why you need money and why you need to feed your family. And eventually the answer is going to be something about what makes you feel happy and what makes you feel sad. And if AI was aligned with our goals, it would have to know what makes you happy and what makes you sad. What's the ultimate driver of your decision making so that it can be the ultimate driver of its decision making. What this means is that we can't build AI that really serves human emotions until we build AI that understands human emotions. And the core thing that machines need to understand is what's in the black box in our brains. They need to understand how the inner representations that mediate between the challenges and opportunities we encounter and our emotional behaviors that we use to respond to these challenges correspond to subjective experiences of emotion, right? This isn't an easy problem, obviously. What makes it hard is that our environments are extremely complex, and so are our emotional behaviors. We express emotion with at least 40 different facial muscles, lots of ways we can manipulate our voice, many ways we can move our bodies, and many ways that we can describe our feelings with language. So to deal with these complexities, as we all know, scientists have historically made simplifying assumptions, like the idea that we can draw simple one-to-one mappings between emotion antecedents like spiders and a few prototypical facial expressions like the so-called fear face. And everything comes down to this, or perhaps everything comes down to valence and arousal, or perhaps we can train people to measure facial muscle movements comprehensively by visual inspection with the facial action coding system. And those approaches have all been helpful in documenting a lot of the broad functions of emotion-related behavior, but they don't generalize well to real-life contexts and expressions or predict real-life behavior, and that's the challenge for affective computing. So we need to go back to the drawing board with modern tools that weren't available to the founders of emotion science and revisit some of those old questions. And in this talk, I'll focus on 3 core questions that I think are really the core questions we need to answer. And the first is, what are the emotional behaviors that we as scientists need to explain if we want to build methods for AI to understand emotion? What is the range of facial expressions and vocal expressions and language and so forth? And I'll talk about how we've recently been collecting new kinds of data and developing new taxonomies based on new data-driven theoretical approaches to emotion. And the second question is, what are the antecedents of these emotional behaviors? Where do they unfold in everyday life? And here I'll talk about my work at Google, where we built new ways to measure nuanced facial expressions at scale in millions of videos and understand the contexts in which they actually occurred across cultures. And then finally, I'll talk about new work that's enabling us to see how these behaviors actually map to people's reported subjective experiences of emotion, which is the kind of work that's needed to build AI that's aligned with our emotional needs. I'll start with the question of what are the emotional behaviors that people actually produce and that we as scientists need to account for. So for the last 5 years, I've been mapping people's experiences, expressions, and perceptions of emotion in the voice, and the face, in prosody, speech prosody, in music, the experiences people have in response to music, and the experiences people have in response to art. And in each of these modalities, we've synthesized first decades of literature and gathered lots of data to try to understand the breadth of human emotional behavior. And this is a visualization of our results for vocal bursts. So we gathered 2,032 vocal bursts, which are laughs, sighs, screams, sighs, grunts, from 56 actors. And we got thousands of participants to judge these expressions in a lot of different ways. And long story short, we found that people reliably perceive at least 24 distinct dimensions of emotion in different vocal expressions, which is obviously a much wider variety of emotions than traditional theories have considered. And we can think of this as a lower bound because it's still only a sample of expressions. And we learned that the emotions that people attribute to these expressions are more precisely represented in terms of specific kinds of concepts like anger and adoration than broad dimensions like valence, whether something is pleasant or unpleasant, and arousal. But these categories, despite being called discrete categories traditionally, are not actually discrete. They're bridged by continuous gradients, linking states like fear, surprise, awe, and realization, interest, and confusion. So now people generally relied on just the 6 basic emotions, or valence and arousal, to represent emotion. So it's critical to go back and ask what these models actually capture. How much of the variance is captured by these ways of conceptualizing emotional behavior? And so now we can use variance partitioning to find out precisely, predicting judgments of the basic 6 from the full state space of emotional behaviors people distinguish, and vice versa, seeing how much the basic 6 predict. And when we do that, we find that the basic 6 captures only about 30% of the systematic variance in what people take away from emotional expressions. This is true for facial expression, as you can see here, true for vocal expression, the taxonomy that I just showed, and emotions reliably reported in response to different videos, and we see this in just about every other modality as well, speech prosody, music, etc. And valence and arousal consistently capture less variance in each case than the 6 basics, about 29% or so. And more recently, we've revisited the facial action coding system because nobody has ever really tested the degree to which the facial action coding system actually captures the muscle movements that drive people's perceptions of emotional expression. And I get that that's what FACS is supposed to do. It's supposed to comprehensively capture all facial muscle movements, but it's never been validated in this way. And so we got thousands of facial expressions annotated by 2 of the best FACS coders I know, and we did variance partitioning. And the FACS codes were highly reliable, with a correlation of more than 0.84 across 53 different codes, but only captured about 1/3 of what facial muscle movements conveyed to perceivers. And that's because humans are natural-born experts, probably, at reading facial expressions, right? Not at trying to infer the underlying facial muscle movements that correspond to facial expressions, which is what FACS is built for. And the techniques that FACS coders learn and rely on are relatively coarse and heuristic driven, right? They're dependent on a lot of extraneous things, like having the right lighting so that you can see certain folds in the skin. And by the way, I didn't set out to knock facts. Just about every researcher I've published is in love with facts, and I like facts. I think it's a good objective way to be able to link certain kinds of facial muscle movements to expressions and perceptions of expressions. So it's not like this is a tribal claim that I'm making. I'm just trying to move people forward to see that facts is not the end all be all. It's not going to capture everything. It captured less than a third, in fact. And so we confirmed, again, that the basic 6, core, affect, and other appraisal dimensions like safety and novelty also capture only a small fraction of what people perceive in facial expressions, which we can more comprehensively map with things like free response. And it turns out that if we have a big enough taxonomy of emotion categories, it captures about 92% of the variance in free response, which of course captures all of the pretty much the basic 6 or affect 13 appraisals. Doesn't quite capture authenticity, so that seems to be a slightly independent thing. And there's things about facts that it doesn't capture naturally, because facts will make distinctions between this muscle over here versus on the symmetric side of the face on the other side, which perceptually doesn't necessarily have any meaning. And so if we're going to capture these expressions in a comprehensive and unbiased way, how do we do that? Well, I think the best way is through large-scale experiments in which we have some semblance of experimental control over the emotions that people experience and express in different cultural and demographic groups around the world. And so that's what I've set out to do more recently with my new private lab and scientific consortium, HumAI. And we've been gathering facial expressions, vocal bursts, speech prosody, multimodal data that's large scale, balanced across all of the dimensions of emotion that we've discovered and more, and captures emotional expressions from around the world, starting with the US, China, India, Venezuela, and Ethiopia, and includes self-report ratings so that we can avoid perceptual biases and confounds by gauging participants' own representations and beliefs about the meanings of their expressions. And I'll show you what some of that data looks like. So I'll start with our data set of vocal bursts. We started by replicating our previous work that I showed you on vocal bursts at a much larger scale, and then we recruited thousands of people around the world to produce their own versions of each expression and report what they themselves think they're expressing. Here are some examples. So we have over 200,000 of these labeled with people's own self-report judgments. We've done something very similar for facial expression. Again, replicating our work, much larger scale, gathering people's own facial expressions around the world and reporting what they themselves think those facial expressions mean. So what we can do with that incredibly rich data is train machine learning models that recognize facial expressions with a lot more nuance than anything that's been available before. For example, this is the first model that we've trained. It's trained on about 190,000 facial expressions, and is able to recognize the expressions that people associate with emotions as subtle as love, or guilt, or contempt, or shame, and awe, versus, say, negative surprise. You can see that these incredibly nuanced differences will make a huge difference when it comes to training empathic technology that understands whether something is desirable like awe or undesirable like negative surprise, even though they're very structurally similar. So we can train models that take video or audio or images and automatically differentiate the more nuanced expressions, facial muscle movements, vocal modulations, to which people tend to attribute lots of distinct meanings. Which brings me to my next topic. the question of what are the antecedents of emotional behavior? When do they occur in everyday life? And here I'll talk a bit more about my previous work at Google, where we built algorithms to detect some of the nuanced facial expressions at scale and examine the contexts in which these facial expressions occurred around the world. So based on my earlier work on the taxonomy of facial expression, Gautam Prasad, my colleague, trained a model that was able to distinguish a variety of nuanced facial expressions, and it worked pretty well for 16 different expressions. And as you all know, we have plenty of algorithms that we can use to classify contexts that occur in video, which means that if we look at enough naturalistic videos, we can now actually compare the contexts that co-occur with many different kinds of facial expression for the first time. And the fact that most of the world now has internet access and millions of people post videos online means we can look directly at the correlations between expressions and many different contexts all over the world. And so we gathered 3 million videos from 144 countries that were uploaded publicly online from mobile phones and that had people in them. And we analyzed whether the contexts in which different facial expressions occurred in the videos were similar or different across cultures. And so to answer that question, we first divided the world up into 12 cultural regions based on language, ethnic makeup, and to ensure a balanced distribution of videos around the world. And each region had over 100,000 videos. So I'll show you the results we get from these regions, but bear in mind that when we look at individual countries that have sufficient data, we actually get similar results. And in each region, we correlated across videos how often each expression was found on average within the video and the contexts captured in the video. For example, here, each of these squares represents one of our 12 regions, and the color of the square represents the correlation between occurrences of the triumph expression, this one here, and the context team sport. And what you can see is that the correlation is positive in every region based on the fact that the colors are red, and meaning that the triumph expression occurs during team sports all around the world. And this echoes classic findings in psychology by Jess Tracy and others that, for example, Olympic athletes from different cultures, even if they're blind, show triumph expressions when they win. But we can now look at this in the context of a much broader space of context expression associations found in millions of normal people around the world. So for example, we can see how specific this association is, and to do that we can compare these correlations across different contexts and different dimensions of facial expression. And what you can see is that the correlation between team sports and the triumph expression is pretty darn specific, but you can also see a broader story unfold with correlations between a number of other expressions and a number of other contexts that are just as remarkably consistent across cultures. And that's easier to see when we normalize within each context because the contexts occur at such different rates. So drawing your attention to that red diagonal here in the middle of the plot, the diagonal is nearly uniformly red because the correlations are so consistent across cultures. And you can see that across every culture, expressions of awe occur in videos with fireworks, toys, and puppies, concentration with martial arts and school, contentment with weddings and birthdays, desire with candy, doubt with protests and police, pain with weight training, and triumph not just with team sports, but also with dance and rock concerts and individual sports. And we've repeated this analysis for over 600 different contexts, and now we can finally ask how well facial expressions are preserved across cultures by correlating these context expression correlations pairwise among the 12 different regions. And we found a minimum correlation of 0.7, which means that about 70% of the variance in actual context expression associations caught on camera is preserved around the world. And the next big question is whether these facial expressions really tell us what people are feeling. We know from our previous study of thousands of emotionally evocative short videos scraped from the internet that the range of emotions people reliably report spans at least 27 dimensions, which is a much broader space than past studies have considered. So to answer the question of whether these correspond to different facial expressions, we've now had thousands of participants in many different countries record themselves while watching each video and then report on their experiences. And so far we've collected 240,000 reactions to over 2,000 videos in over 10 countries on 5 continents. Here's one example.
Oh, yeah.
So you can get the sense of how rich these are. So by analyzing these with machine learning, we can not only compare emotional expression to experience, but we can model moment-by-moment variations in expression and really capture the deeper nuances and dynamic properties of these signals. So we decided to run models to find out how nuanced these expressions really are. And it turns out that at the aggregate level, we can predict a wide range of reported experiences from facial expression. So on the left, you can see the experiences that participants reported after watching each video. And on the right, you can see that the average predicted experience from expression along 12 dimensions that we were able to differentiate, which included things like surprise, fear, sadness, empathic pain, disgust. And so expressions do actually convey aspects of emotional experience. We can find almost all of these expressions in both Western and, for example, Japanese study populations. So these are some of the highest loading examples on each dimension. I'll leave this up for a second. But there are big differences between cultures in the average intensity with which these different emotions are expressed. So Westerners, for example, including in the US and the UK and most Western countries, express amusement, disgust, joy, and romance with at least 60% more intensity of facial movement on average than people in Japan, for example. Now, it's extremely important to take these differences into account, because if you don't adjust for the differences in expression intensity across cultures, it looks like only 16% of the variance in the expression to experience mapping is preserved across cultures. But if you take intensity differences into account by normalizing the measurements, an overwhelming 81% of the variance in the mapping from experience to expression is preserved across cultures. And this is for the US versus Japan, which were the most distinct cultures that we could find. So again, if you take these differences into account, you can often predict emotional experience from expression within and across cultures pretty accurately. So here are a few examples from top to bottom. You can see the stimuli, the reactions, one in a Western country, one in Japan, and self-reported emotions. And finally, the emotions predicted from the expressive reactions by our model in the West and in Japan. So overall, we've begun to put together a taxonomy of emotional behaviors, learn how those behaviors map to different kinds of antecedents of emotion, and how they correspond to emotional experiences. But this taxonomy is still provisional, and like, for example, the periodic table of elements, which I think is one kind of analogy for what the taxonomy of emotion could be for emotion science, I believe it's just a necessary step toward a more cumulative science of emotion and toward developing the ingredients of empathic artificial intelligence. The next step is to understand the causal functions of different emotional behaviors and how these building blocks of our interactions and relationships come together normally, and how they can vary across individuals and when those variations lead to dysfunction. And the next step to addressing these questions in a cumulative way and making consensual progress in the field is to have rich data that we can use to build computational models. So what we've been doing is collecting the data that's needed to support a cumulative science of emotion, a unification of emotion science and affective computing, baseline models that allow us to measure emotional behavior at scale, and we've been providing these tools to scientists to advance our understanding of human emotion, and to industry teams that are looking to develop empathic technology that adheres to our ethical guidelines that we're developing. And beyond myself, we now have 4 AI researchers, a psychology researcher, and a number of scientific advisors involved. And we're open to more partners and collaborators in academia and industry who can use our data to develop beneficial empathic AI. We also have funding for more AI researchers if you or anyone you know would be interested in joining this effort. To find out more, check out our website, hume.ai. You can also find links to all of my papers that I've discussed on my personal website, alancowan.com. Thank you so much for listening.
Hey everyone. I just wanted to ask before we got started, was everyone okay if we record the session? Any objections to that? Okay, great. And I'll give it a few more minutes. We'll see if like Alish can make it. So we'll try to start at 5 after. Okay, looks like we have everyone here and I'll get started. So first off, thank you all for attending the first international workshop on effective understanding in video at CVPR and joining us for our invited speaker panel. I'm Gautam Prasad from Google and one of the organizers of this workshop. We'd like to extend a special thanks to our invited speakers for their talks, which you can view on demand on our YouTube channel. We'll start this panel with a few prepared questions and then go to questions from the audience. To ask a question, please feel free to raise your hand in the Zoom call, use the chat feature in Zoom, or use our Google form. To begin, I'll introduce all our speakers and then we'll jump into questions. Alesh Martinez is a professor in the Department of Electrical and Computer Engineering at The Ohio State University, where he is the founder and director of the Computational Biology and Cognitive Science Lab. He recently demonstrated the existence of a much larger set of cross-cultural facial expressions of emotion than previously known, and the transmission of emotion through changes in facial color. Daniel McDuff is a principal researcher at Microsoft, where he leads research and development of affective technology. Daniel's work on non-contact physiological measurement helped to popularize a new field of low-cost health monitoring using webcams. Previously, Daniel was director of research at MIT Media Lab's spin-out Affectiva and a postdoctoral research affiliate at MIT. Chunjun Lee is a postdoctoral scholar in psychology at Dartmouth College. She is part of the Social Computational Representation and Prediction Laboratory, working with Professor Mark Allen Thornton. Before joining Dartmouth College, she worked with Professor Ralph Adolphs in the Emotion and Social Cognition Lab at California Institute of Technology, where she earned her PhD in social science. And finally, Alan Cohen is an emotion scientist leading a scientific consortium and technology company called Hume AI, and a former researcher at UC Berkeley and Google. His research uses computational methods to address how emotional behaviors influence the course of social interaction and relationship building, and how they bring meaning to our everyday aesthetic and moral lives. To begin with, could we go around to all of our speakers and get a bit of an introduction and a summary of your main points in your talk and how they relate to our workshop. And we could start with Alish.
I'm sorry, just want me to give a summary of my research, right?
Yeah, and how it relates to the talk.
Yeah, sure. So one of my interests right now in the research that we do is the recognition of intent, and that obviously includes emotions. Emotions is part of understanding the intent of others. Intent is considered one of the hallmarks of human cognition. It's one of the things that separates humans from most of other animals, not all, but most of other animals. Some apes also have recognition of intent, and there's debate on whether some other animals also have recognition of intent. But basically, this is a component of what's usually called in psychology and neuroscience theory of mind. And theory of mind is the ability that humans have to think about what other people are thinking about. So I can be thinking about what you guys are thinking about what I'm thinking right now. And this is a very profound iterative process that can go on forever. Computers in recent years have made amazing advances, or computer science, I should say, has made amazing advances, in particular in computer vision and machine learning and NLP. But we're still, eons away from being able to develop AI or computer systems that are able to behave like humans in a more cognitive, high-level cognitive way, as the recognition of intent and other parts of theory of mind. So I'm very interested in that. In my lab at Ohio State, we do very interdisciplinary research. We do research in, obviously, computer vision. I've been very involved in CVPR. We actually organized CVPR back in Columbus in, I think it was 2014, if I'm not mistaken. That was a few years ago. But I've always been very involved with CVPR and the other conferences like CCV, etc. But I'm also very active in the neuroscience community and less active, but I'm also sort of active in the cognitive science, cognitive psychology and social psychology communities, where I also attend some conferences and we present our work, because our work has implications in all these different areas. So we bring in a very multidisciplinary approach in trying to create models, computational models, that emulate what humans do. And for this, I think it's extremely relevant to understand not only psychology, the literature in psychology, but also the literature in neuroscience. So psychology, you can interpret it. And this is why I talk about a little bit of what I discussed in my talk. Psychology is what David Marr used to say, the high level of the 3 levels of implementations that he had. Right, the computational level, the very high level description, whereas neuroscience is the implementation level, right? And when you create the model, there is a huge gap between these two different levels, and that's a little bit of what we do. We try to work at all these different levels with these models. And as you said in the introduction, in the past, in 3 different PNAS papers, we've introduced a number of visual expressions of emotion that is much larger than Darwin and Duchenne and Darwin had proposed. And even, I mean, this is a little bit unfair because even Aristotle had proposed some of these basic visual expressions few centuries before them. But at any rate, Aristotle and Descartes also proposed them. But we showed that there is a much larger number of visual expressions, almost universally used. I could say universal because we test every single culture, but we tested 35 different cultures, which is pretty large number. I want to make a comment here that when I say they're universal, I mean that about 35% of the time people understand that production and of that visual expression as having a common meaning. Now, 35% is much, much higher than random or a chance. So it is a scientific finding that's very important, but that doesn't mean that when I look at a specific person, a single person, I am able to recognize that person's emotion from just a single signal like a facial expression, meaning facial muscle articulation, by the way. There are so many nuances there's this additional 65% of the data that does not align with that. So it is, in my view, impossible for a number of reasons that we discussed in a paper not too long ago, about a couple of years back, in the journal Psychological Sciences in the Public Interest, with Lisa Feldman Barrett. Actually, Ralph Adol was also involved in that, Stacy Marcella and others. So I really encourage people to look at that paper, because we discuss, the limitations of understanding emotion. And then we had, as you mentioned, that other paper, we showed that when people experience emotion, let me back up a little. So when we experience an emotion internally, we experience a number, or our central nervous system executes a number of computations, right? That's what experiencing emotion really is. If you believe that this system is nothing else than an execution of a number of computations, then when that happens, some of these computations actually is the release of peptides, neuropeptides. The most famous neuropeptides are hormones. And then what that does, it changes the blood flow and the blood composition. And it turns out that the face is innervated with a huge number of blood vessels on the surface of your skin. So your face actually pulsates in color when you experience emotions. And it's not like the big flush that you get sometimes when you're embarrassed, right? They're very tiny pulsations in color, but we've shown that PNAS paper that you can detect over 20, I think, emotion categories just based on the color alone. And this is actually more reliable than detecting or working with the facial muscle articulations. We've done work with body pose as well. We've done a lot of work on context. Context is extremely important, especially in video. So I encourage people to work with context. You cannot understand the facial expression, meaning facial muscle articulations, or even the color or the body pose in isolation. You need to understand the context, the contextual information around that person, as well as what that person is, where that person is situated in their culture, their background, who are they interacting with. All of this is important. And then moving back to a broader picture of recognition of intent, we want to understand the biological motion of agents to understand whether actions are done intentionally or non-intentionally and what they mean. And recognition of intentional actions is extremely relevant. So you can think in the US judicial system, for example, if you commit a crime, say murder, if it's a non-intentional murder, that's called manslaughter. And most people don't even go to jail for that. But if it's intentional, this is either second or first degree, you're going to spend the rest of your life in prison. So that's how important intent is in human law. So recognition of intent, to me, it's this next big step.
Awesome. Yeah, thank you. And maybe next we could do Daniel for an introduction on his talk and how it relates to the workshop.
Thanks. Yeah. In my talk, I mostly talked about physiological measurement, in part because I completely agree with Alex in terms of what other things beyond facial actions can provide in helping us understand emotional states or expressed emotions. So blood flow, changes in heart rate, changes in respiration, I would say are equally as useful as measuring facial actions for the communication and understanding of affect from when you're looking at an individual. And so we've been working a lot on vision techniques for recovering these signals, in part because it's using the same modality as we would use for detecting facial actions. And also, again, building off what Alex said, video gives us, unlike many wearable sensors, gives us context in some cases. So we can see the scene or the environment of the subject, their other pieces of information that can help us interpret what's going on. So for various reasons, being able to do measurement from of physiological information from video is interesting for several applications, and we're mostly focused on health and well-being applications, where we're looking to use these measurements of physiology both for detecting vital signs which might be used in traditional clinical contexts, but also expanding that to look at affect, and signals that might not be traditionally used in clinical settings like stress or measurements of autonomic nervous system activity, and how we can potentially expand the way that we can think about vital signs. Vital signs could be many more things than simply heart rate and blood pressure. So that's why I focused primarily on physiological measurement, and within that we have a big focus of using synthetic data, again for several reasons, to help train our algorithms. One is being able to create data sets with a large amount of diversity, both in terms of motion, illumination conditions, demographics of the subject, clothing, all of those types of parameters. But also synthetic data gives us the ability to create very precise alignment between our input signal, which might be RGB images, and different types of ground truth. Like we can get very precise depth information, very precise segmentation information, but also very precise physiological signals, which we use to drive the avatar or simulation. So those things are very interesting. In terms of what we're applying that to is looking particularly at longitudinal measurement of affective signals. So a lot of the work, a lot of work in the past is focused on more sort of instantaneous measurement or measurement over short time periods. And this is something we did a lot at Affectivo, was looking at people's reactions to, for instance, like video ads, where you're analyzing someone's reaction for, say, 30 seconds. But in terms of when we think about well-being and how affect plays a role in well-being, I think that's only really possible to understand if you can observe these changes longitudinally and be able to personalize algorithms to particular individuals and look at how an individual changes over time, or their behavior changes over time. So we've been doing some longitudinal studies to look at diurnal patterns and time varying patterns across large amounts of data in situ. So by deploying some of these vision-based algorithms with people's permission to track both facial expressions and physiology in situ, we've been able to find some really interesting patterns, both in physiological changes across the course of a day, but also facial expressions or expressed affect across the course of a day. And ultimately, we want to be able to provide people with tools to help them manage stress and manage affect. But the sensing is sort of a foundational piece that we're building to enable that.
Thanks a lot, Daniel. Chu Jen, would you like to give your own introduction?
Yeah, thanks, Gotham, for your introduction. So I'm Chu Jun. So in my PhD work, I focus on understanding how humans form trait impression about other people. For example, now we're looking at the screen showing 4 people's faces here. So I study how people form impression about their personality just based on looking at their faces. So in one of our recent work, we found that even though people can use a lot of words, like extroverted or intelligent, or different words to describe other people's traits from their face, but all this trait impression can be summarized by only 4 dimensions, like their warmth, competence, femininity, and youth. So in my postdoc training, I have extended my interest to understand mental states, like how people infer other people's mental state, including affect, like emotions, and other broader cognitive processes like decision-making or planning. And then I also try to extend the stimuli from more artificial ones, like the aesthetic photo, face image of a person, to like more naturalistic videos. So in the talk, I have mentioned how the process of inferring other people's mental states and inferring their traits are connected and even causally infecting each other. So I think these two human cognitive processes are also important for computer vision or machine learning, because I saw some recent paper trying to like build an algorithm that try to teach an agent to understand other agent by capitalizing on this human cognitive processes components. Then in a broader team effort in my postdoc lab, we're actually trying to also apply more recent development from machine learning and computer vision to see whether we can understand how people interact in natural environment. For example, recently we tried to apply algorithms that annotate body pose when people interact naturally. And we want to understand whether from those pose feature, we can tell how people synchronize when we interact with each other, or how people use this body motion pose to inform how the other person's personalities are or their mental states are. So this is the first time I participate in this conference, and I'm excited for it because I want to learn more new stuff from computer vision and machine learning to see how we can apply those new development to our psychology and brain science research to understand human behaviors.
Thanks a lot, Juchun. And Alan, would you like to give a bit of an intro?
Sure. Thanks, Gautam. Thanks, everyone, for coming. As Gautam noted in his introduction, my work is focused on developing new ways of studying human emotional expression and emotional experience. And I've taken a more data-driven view of how you ask those questions and how you ask what people take away from facial and vocal expressions, what they mean in terms of self-report, how they correspond to different antecedents in the environment, how universal they are across cultures, and how you build models that interpret these behaviors. So that was basically the focus of my academic work under my PhD. I did a stint at Google as a visiting faculty researcher with Gautam, where I helped establish affective computing efforts. And on the industry side in general, I ended up advising other companies during my PhD as well on how to build empathy into AI technologies. What I saw time and time again over the years, both in academia and in industry, is that there's a search for better data to develop more cumulative theories of emotion and build technology that can make predictions about what people care about, what people take away from perceptions of emotion, how that influences social interaction, how emotional expressions can potentially give you a window into people's health, well-being, as Daniel was noting. So more recently, I left to form a private lab called HumAI, and our goal is to do large-scale experiments to gather unbiased data with many cues to emotional expressions and people's self-report, and to be able to make predictions from people's emotional expressions that are relevant to relationships, that are relevant to people's health, and so on. And so what really excites me about this workshop is that we're taking video data and we're predicting emotional behavior. And I think that's a really nice direction. I think we should, in general, move away from sort of pre-selected features, more toward directly predicting things that are of relevance that we ultimately want to understand, like what people take away from emotional expression, like what they're feeling. Very interested in integrating things like heart rate, as Daniel is doing, and like facial coloration. I think what we really should do is think about how we can find the right data to be able to build predictive models from all of those things and see the extent to which each of them predicts psychologically relevant and significant features like self-report and health and so on. So very interested in discussing this further.
Thanks, Alan. Yeah, and thanks everyone for their intros. To begin with, one question for the whole panel, kind of building off what Alan talked about, is in the last few years, we've been able to use these facial expression data sets that have been publicly available and are necessary to do deep learning. And now to push this field forward, we're trying to look at other signals, whether they are in modalities, kind of like physiological signals or simulated data. What do you guys think are the bottlenecks in creating rich data sets, and how should we prioritize what types of data we need to be able to model affect better in the future? Yeah, and anyone chime in, feel free to discuss it freely.
I'm happy to go first. I think we need that data, there's no doubt, but I want to caution people on how we create that data. Self-report, because emotions or affect is difficult to determine. Self-report is not a good measure of the emotion that someone is actually experiencing. It's still unclear how we interpret our own emotions. And we all obviously interpret them differently depending on the situation we're in, the culture we're in, the context, etc. So, if you want to play a game, right, with a family member of yours, maybe at night switch the decaf coffee for regular coffee and see how they become anxious and they feel like, oh my gosh, I'm really nervous because of work, or something happened to me today. And no, you just had caffeine. It's very difficult to interpret the signals, these internal signals that occur in our body. So self-report is not ideal, and the underlying condition is very difficult to determine from physiological signals, because we don't know what the actual experience is. So we cannot find the actual correlations or features, physiological features that only occur for specific affect conditions or emotions and not for others, right? So again, I would encourage people to read that PSPI paper. We give some ideas there of things that we think should be done, but we need data for certain. We're data scientists at the end of the day. So I really encourage people to build these data sets, but be cognizant of those problems.
Yeah, I think those are great points. I really like what Alan presented in terms of, bringing in context to some of these data sets. And I think the more that we can do that, the better. And context can look, can have many different sort of properties. So the more that we can get the situation that these videos or these data are occurring in, the better. And even though self-report of emotion might be difficult, self-report of what people's intentions are in specific situations, or other pieces of information to help with the interpretation of what's going on. So people can often report what they in a particular situation, what their intentions were, even if they're not able to report what they were feeling. And I think these types of other information that we can bring into how we model just the physical appearance of the face and how that might be interpreted can be very valuable. And then also, the more that we can get again, longitudinal data or data that allows us to look at how to do a better job at normalizing for particular individuals or particular cultures or particular contexts. So it may not be that we need lots of longitudinal data of a specific individual, but longitudinal data within specific contexts or situations could be very valuable. So all of this is a long way from the types of data sets that we have had in the past and even currently have, which are typically short videos or even just images of faces.
Yeah, I mean, I would definitely agree. Self-report is not the only thing that we need. We probably need something to decide what we need, right? We need to decide what it is that's relevant to collect. What are we predicting? Does self-report predict it? Can we capture it as well with facial expression? In some cases, you can't really do any better than self-report. For example, if I ask somebody, hey, was that a satisfactory response from Alexa? And it's an actual context in which you want to know whether somebody felt like it was a good or a bad thing that they're feeling, then it's probably better to trust what they say than to say, well, you were smiling, so I think you're probably wrong about that. Actually, I think that was a satisfactory response. So I think in some cases, self-report is kind of the sine qua non, and we need to go by something. We need ultimately to defer to people's own priorities, their own values, their own, what they want out of technology. And I think that has to ultimately guide our development of technology. If we could predict the things that people actually say they want from their behaviors, I think that would be the gold standard.
Yeah, I'm happy to join too. So these questions actually remind me what I was thinking about when I was listening to Alan's talk. Well, first of all, very great, cool data sets, Alan. I especially appreciate your effort to collect cross-cultural data. So I think one challenge is how to collect data when people are naturally doing it. Like when people know that they were being watched when they record themselves to watch the video, I think they also react a little bit different. Like this in psychology research, we already know that even when you see on the computer screen, there are two dots that looks like an eye, the eyes looking at you, your behavior changed. So I think one challenge is how to collect big data in a natural way without violating people's privacy. And the second point, I think, is collecting multiple module data is also important. Like we can see people or infer people's emotion from the face, from the body that we can see. But actually in the literature of emotion embodiment, we also say that we feel our emotion in different part of our body. Like we sometimes feel it in our chest, we feel it in our tight belly, and we feel it in every part of our body. So actually that related to Daniel's work that maybe we want to combine them with like physiology, like measurements. So with this multi-module data, we might be better, like with this rich data set, we might be better at like predicting people's emotions, so understanding our affective feeling.
Oh, awesome. Yeah, thank you so much for all those cool answers. Another question that we were thinking about is we can use a lot of affective understanding technologies in applications such as healthcare or human robotic interactions. And amongst the panel, what do you think are the most exciting applications, and how will that inform like what attributes around affective annotations you want to collect, or what types of models you want to build based on like what would be most likely to help people or to be rolled out in practice?
I think we should go in reverse order now. So I'll let Shushun go first.
Would you mind to repeat your question, Gautam?
Yeah, like what applications of affective technologies are you most excited about?
Oh, cool. Yeah, definitely excited about how to use it in like psychology research to understand human behavior. As I mentioned, we try to apply algorithm that automatically annotate body pose from videos. But then actually we face a lot of difficulties. First is when the body is outside, like in the Zoom call, you only see my upper body. And then there's some algorithm that try to predict other parts of my body's pose. So like when the body is only part of visible, they're supposed to challenge how you estimate the whole body pose. There's also when someone just walk across and so it's covering part of my body, and that's also challenging. Another one in my research is I want to understand like how people keep track of one target when they're watching a video. So the other question is how do we try to track the same person's pose, like identify this is the same person across different cuts and scenes. We kind of try to overcome this by combining the pose algorithm with the face identification algorithm. So we see whether, like, for example, there's two track of body pose, and then we see at the same time the face identification for these two track, and whether we can combine these two algorithms to tell us which track belongs to which person. Yeah, so I think if there's like, because like now in psychology or brain science research, we really want to extend our traditional stimulus set to more natural, complex one. But we need a tool to identify those stimuli. For example, if I want to study video, I can just pick any video that can satisfy my, that can give me whatever result I want, basically. But because like if I want to see whether people update their trait impression then when they're watching video, right? Then I can just find videos that where people's trait impression change a lot, or where they so the problem is, okay, now the stimuli is becoming more complex. How do we sample it? So one solution that the computer vision community might help is if we can say quantify a lot of feature of this video, like effect, like how variable the effects are from these videos, or pose, then we can just quantify them as like dots in this high dimensional space, and then we can representatively sample them without any bias in selecting this stimuli. So I think that would be very helpful. Yeah, thanks.
Yeah, I just want to plus one that I guess, well, the reason I got into this research is to improve metrics for psychology. I mean, there's so much you can do in psychological research with unbiased measures of people's emotional behavior, if you can apply them at a large scale without lots and lots of manual annotation, which is usually the limiting factor. And, you know, there's, just to name a few, I mean, developmental psychology, understanding risks for developmental disorders, understanding the development of personality, and understanding the development of you know, personal behaviors and what you prefer later on in life. I mean, there's so many questions in developmental psychology, and so too for, you know, mood disorders, understanding what are the triggers of bouts of depression, how can we react to them faster, how can we measure mood disorders for the sake of developing treatments more efficiently, because right now our measures are not very reliable. We create more passive measures. There's lots of technological applications that are very interesting. Developing digital assistants that are more empathic, that can understand what you want when you say you're frustrated, change their last response. When you are tired, you can speak to you more quietly and gently, etc. Social robots, very similar. So many applications. I guess from like a long-term standpoint, I'm most excited about the idea that we could potentially build AI tools, models that are optimized for people's or proxies of people's emotional well-being, or, you know, our values, what we want to feel in different circumstances. Because right now, I mean, we build these algorithms that are optimized for human behaviors, like click through on ads or engagements, or, you know, the first thing that we click on when we're searching. There's you know, a risk in that that's inherent in optimizing for human behavior without having any visibility into what people are feeling, which is that you could be optimizing for behaviors by increasing the wrong emotions, right? So for example, even in just something as simple as search, and I think search is sort of a generalizable thing, everything kind of comes down to it. In the realm of search, search algorithms can get depressed people to click on things earlier by surfacing results related to seeking therapy. That's great. But if the search algorithms can also get depressed people, people who've recently searched for antidepressants, for example, to click on things earlier by surfacing results that are likely to increase the risk of self-harm, which we know that people with mood disorders are at risk for. That's a negative. And if you're just optimizing for behavior like click-through, you don't know which one the engine is learning to do. If you have some proxy for well-being that comes out of people's language, that can be linked back to reports of their own well-being or their actual preferences, and you can prove that that proxy generalizes to different kinds of people across cultures. I mean, that's ultimately the goal. So I think in the short term, incorporating emotional behaviors into technologies that can use them to optimize for things like the treatment of developmental disorders is very interesting. In the long term, it's going to be optimizing for things that involve emotional behaviors as a proxy for well-being and as a proxy for meeting people's goals and preferences.
For me, the things that I'm most excited about, touch on some of those aspects that were mentioned before, but particularly focus on giving individuals, the ability to help understand more about how things in their life kind of affect their behavior and affect their well-being. So to take Alex's example of the coffee as a sort of just as an exemplar, there are many things in our lives that affect how we behave, and often it's through trial and error that we discover the things that work for us, and we don't have many tools to help us necessarily identify those things, and sometimes we're not even aware of the change, how things affect our behavior, or if they affect our behavior. So for myself, looking at this type of data for myself over periods of time, I've identified patterns that show that I'm more likely to express negative affect in the afternoons than in the mornings, because I've looked at my own longitudinal data and I've seen this very repeatable pattern. That was not something I was aware of. I didn't realize that my tiredness across the course of the day meant that I physically appeared differently to people. I would be more likely to communicate with more negative, with expressions that might be construed as more negative in different, in the afternoon versus in the morning. And we have to be very careful about how this technology is used. But I think, we have tools for tracking health metrics and looking at how our exercise impacts our heart rate. I do believe that there could be similar tools that could help us understand how our lifestyle parameters, impact our well-being. And one way to give people feedback on their well-being is to allow them to, be able to access this data and understand it in their context and interpret it for them, and then use it to help make changes that they want to see. So most of what I want to see is this technology in the hands of individuals to use it to help them. Some of the large scale applications, I certainly can see how it could be used in search contexts and other things, but also I'm very cautious about how we would want to bring these very personal, often very personal pieces of information into large scale systems. Yeah.
So I Basically, just gonna repeat very quickly some of the points that I agree with strongly. I agree with all of them, but I think that the application of trying to first understand um, and then help diagnose psychopathologists is an important one. The heterogeneity of psychopathologists make it really hard to diagnose. So it would be certainly very helpful to understand more about them. And there is a debate of how much we can help and how much we can harm. So it's a debate that we need to have, but that would be absolutely extraordinary if we could be of help in that regard. To me, in particular, the most important one is the recognition of intent, as I mentioned at the very beginning. And anything that you do, well, I say anything, but almost everything that you do with, well, probably not us, but the general public do with computers, cell phones, tablets, any device that they use, is they are giving information to that device, and the device needs to understand the intent of that user, right? And someone has mentioned search as the quintessential example of that. When I write a query in search, or I say a few words to my device, I want my device to understand my intent. What do I actually want? And that is a really hard problem. And by just studying the syntactic and the semantics of a sentence or a few sentences, you are not guaranteed to get to the intent. You need a lot of other variables, especially affect, but also what we were talking about earlier, right? That contextual information, that cultural information, that situation where you're situated in. All of that is extremely relevant. And I'd certainly love to have a lot of data sets that can start helping help address these problems. And someone has mentioned earlier about self-report of intent. And I think this is a fantastic idea. This is what we've been trying to do, right? Let people tell us what their intent is, because it's very clear, and then try to discover what are the affect variables that are relevant for that intent.
Well, thank you all for the answers. I'd like to open it to any of the audience if anyone has a question live on the Zoom that they'd like to ask. Okay, I can ask another one actually. So I think one thing that has, I think, been complex to understand is there's like arousal affect, there's emotion categories, there's like, in I think a lot of your researchers, you discovered that the landscape of expressions and emotions is much more complex, like even with the states versus traits and everything. What should we study? Like, what have we discovered are the most important things to study? What is easiest to study, like most replicable? How do we look at this complex landscape of how we describe emotion and affect? And what's the way forward? What should we be doing now that we haven't been doing in the past?
This is a very contentious topic. I can give you my 5 cents on what I think we should do, but obviously we need different viewpoints because this is under debate, right? What our research has shown is that emotion categories or affect variables like valence and arousal are actually not what's implemented in the brain, in the human brain, I mean. And that goes back to my implementation level of David Marr's architectural levels. So what we have shown is that the dimensions, if you will, of the computational space that we have in our brains, meaning the algorithm, basically. So if you considered cognitive or computational space, where there are certain dimensions that the brain computes and then extracts the information from that multidimensional space. Then the dimensions are the facial muscle articulations, the changing facial color that I've alluded to, the body pose, the biological motion of that agent, the interaction with other agents, the contextual information, the situation. So all those are important variables. And then when you run these psychological experiments, it's actually perceivable as either motion categories or continuous variables like affect variables, arousal, and others. But we have shown, and we have some papers on that, where we have shown that those are actually just illusions in our model that actually arise from those underlying true computations that the brain does. I know others will disagree, but this is a very interesting debate that we're having in the scientific community right now.
I'm happy to go next. So, in my view, we ultimately need to be able to predict something that's of relevance to people, right? And so the key thing then, I think in the context of like mood disorders, it's pretty obvious. And the measures for mood disorders contain things like, are you feeling bad? Are you feeling good? Basically self-reported mood, right? And so ultimately the answer there is to develop treatments that make people feel better. And that depends on self-report as well. I think if you go to like Russ Poldrack's research, he compares a lot of different self-report methods with a lot of different task-based methods and behavioral methods. And the self-report methods have the most predictive value by far. They predict like 90% of the variance, and the task-based methods predict like 10% of the variance. And whether people are going to succeed in like losing weight or quitting cigarettes, or, the things that people really want to do, right? And these things are a function of day-to-day behavior. You can get self-report from ecological momentary assessment methods, where people are buzzed on their phone and they say like, I'm feeling good right now. And that's very predictive of the onset of different mental strains and disorders and symptoms. And so we really need to get a handle on the subjective, I think. We also really need to get a handle on what are the outcomes that we're interested in. I mean, people want to actually quit smoking, and they want to, whatever their goals are, and how we can actually build technologies that have some predictive value in that domain. So if the goal if people want to quit doing something, it's not always clear where you separate their long-term intent from their short-term intent, right? So if they're pulling out a cigarette, their short-term intent to smoke, their long-term intent may be to quit smoking. And so those could be at odds with each other very often. And so what you want to be able to predict is long-term well-being and long-term intent. Those kind of go hand in hand. People intend to improve their well-being over time. They want to be more satisfied with their life. And they have different ideas about how to make that happen. And so we need to get closer to that. We need to get closer to the measures that are of relevance to people, and understand what it is that predicts those measures. What is it that predicts a healthy relationship? I mean, Gottman and Levinson's work, emotional expression was really at the center of predicting whether married couples would stay together, whether people who were dating would get married. And being able to make that assessment in a way for people to use it that is useful to people. I think you really need to have the outcome data or some proxy for it that's closer to what the outcome data would tell you. So people's conversations, and you have a measure of empathy, people reacting to videos, and you have a measure of whether they actually liked the video or not. And more specifically, what are the different feelings that it evoked that caused them to either like it or not? Because in some cases, you want to feel sadness. If you're looking at your friend's post on Facebook, and it's about a tragedy that happened to them, it's in your interest to feel sadness so that you can express sorrow, and it works better from a social interaction perspective. And so it's not, of course, always just about happy, sad. It really is understanding people's affect and whether it's appropriate to the context that they're in. And so we need to understand what those contexts are. We need to understand what the outcomes are, whether they're good or bad. And we need to have some embedding. Basically, I think to get all of that, we need an embedding of facial expression that predicts for example, predict perceptions of facial expression. You know, like like one of the things that should be predicted by facial muscle movements is how people perceive those facial muscle movements reliably across different people, right? And if there's something missing there, if you can take two facial expressions that have different perceptions because they have different facial muscle movements and everything else is held constant, you need to make sure that whatever you're using to measure facial muscle movements can capture those perceptions, or whatever else that's reliably predicted by the expression. And so I think we have some ways to go before we get there. We can derive those embeddings. I think we need to derive those embeddings from the outcomes from psychologically relevant measures. I think that and this will be very controversial, but I think that facts is a good start. I think it only really captures about half the variance in facial muscle movements, and it hasn't really been validated fully. But so I think like a good start would be to derive a measure of facial muscle movement that truly is comprehensive and unbiased, and then be able to apply that on a large scale, or a measure of body movements or a measure of emotion in the voice, and be able to apply that at a large scale. Because generally speaking, you don't have enough data to go straight from like an raw audio signal or raw video signal to an outcome variable like depression, for example. So you need some embedding. You need some embedding that captures all of the relevant variance in people's vocal emotional expressions or facial emotional expressions, so that you can apply it to data that's not millions or hundreds of thousands, but maybe tens of thousands of samples, and be able to say, this person with depression is responding well to this drug, and we can tell based on their facial expressions. And as a proxy, if you look at people's self-report, it predicts their depression level as well as self-report does, or maybe better than self-report does. Even the self-report is built into the measure of depression. Maybe you can actually do better and more reliably with a passive measure of facial expression over the day than you can with self-report in a therapy session, which is localized part of the day. So yeah, anyway, data with actual outcomes, more data-driven approaches would be my general inclination.
Yeah, so as Gautam, you mentioned, like it feels like the mental state or fact space really complex. Like there are so many different elements in here. We have like those emotion words that we're familiar with, but also other cognitive processes that we consider as mental states, like planning, decision making. So I think one approach, as you mentioned, is understand the dimensions. But when we say dimension, they're actually groups of affective words or mental states that explain most of the variance in your data set. But then this feels like the main trend, but it's important to understand the main trend, but also there are like different affected states or emotion that might not best categorized in any of these main trends, like maybe Schadenfreude, for example. I don't know whether that's the case, but like this type of very special or subtle emotions, they may not belong to any of this big category or dimensions, but is this like they also add to like they make our life more colorful. So it's important to understand these main dimensions, but I also think that it's very interesting to understand this like outliers that does not belong to the big pictures. So I think it's very hard to answer the question of what the field should do, but I feel like if like each researcher study the topic that they're interested in and like really do it in like a transparent and like good research practice, and then we can build this like knowledge accumulatively. Yeah.
Yeah, I agree with many of those points. The only other thing I'll sort of add, which I think is maybe similar to some of the things that have been talked about, is that there are in our research looking at longitudinal and diurnal patterns in expressed affect, we've seen lots of variations. Like in social contexts, when we know people are with other people, dramatically changes their facial displays. And so and these feel like things that we should be able to build more computational models for, and there's certainly a lot of research on analyzing facial expressions, for instance, in group interactions and things like that. But it's if we can build data sets and models that help us disentangle again the intention of these observed behaviors. So am I smiling because I want to build rapport with you, or am I smiling because something you said delighted me? Am I smiling to be polite? Like, the same action occurs in many different contexts with many different meanings, and it feels like these are things that we can answer some of these base rate questions with data that we already have. So I'm not sure what the right model exactly for emotion is, but coming from the side of the field that's looking at building tools to measure observable things and then do that at scale, I think this is one thing that we can certainly do more of, is to answer very fundamental questions, which are about just the base rates of these different expressions under different contexts. And Alan's work is a great example of that. And we've done some work also looking at cross-cultural, propensity to observe facial expressions in in-group and out-group settings and things like that. And I think there's just that would be very useful for informing, I think, the models that we can develop, which may be our taxonomies for different emotional states or things like that. But there's still a lot we can do, even if we don't have perfect models for emotion.
Well, thank you for that. And I know we're at the hour. For the workshop, we have a few minutes that we can go in over it. But if you have to leave right now, please feel free to do so. I know there's just one final question. So I thought we could do that, but feel free to drop off if you have a scheduling conflict. So the question is, it seems like everyone agrees with data sets being very important, and kind of building off what Daniel was talking about with computational models. In terms of methodologies and techniques, what are important next steps we have to make in order to progress on affective understanding?
I mean, you can take this in many directions, but I'll go ahead and take it in the psychology direction because I'm a psychologist. We could work on, of course, algorithms and models and so forth. I think one thing we really need in the field are methodologies for valid representations, extracting valid representations of psychological constructs like empathy, right? So that we can build the AI technologies that we want to build. If we want to build empathic digital assistants, we should have some representation of what empathy is and how you can generate data where you can actually measure empathy. And so there's some preliminary psychology work that needs to be done there that I'm hoping to do. And you can get that data from conversations between people and asking them what the amount of empathy they have, or you can look at objective metrics like the success of their relationship as proxies. But I think, we really need carefully designed experiments. I think the focus on public data or posed data, I think poses the problem that you don't really understand what's going on from a psychological perspective, because you don't have psychological control, the kind of control you would have in a controlled psychological experiment. And so I think there's a lot more large-scale experimentation that needs to be done so that you can take these two fields and really bring them together. You can have a valid psychological construct and you can predict it using machine learning. And I think that's the sort of work that has really been missing, in my opinion, from a lot of what we do, because there isn't much interaction between the affective computing and psychology. I realize now that we have a few people from the psychology world, which is great. I think that that's an incredible development, that we can bring those worlds together. But I think that the reason that there hasn't been that merger is because the data being collected in affective computing is not really being collected in a way that you could answer questions in psychology with it. And the data that's being collected in psychology isn't really being collected in a way that you can answer questions in affective computing with it. But if that's the case, how could you predict valid psychological constructs with the data that's being collected in affective computing if you can't publish a paper in a psychology journal that says this is a valid prediction of X, Y, and Z? So I think whether those fields are brought together will be a good proxy for whether we've brought sort of new methodologies to bear on really important questions in affective computing.
Yeah, completely agree with that. I think that's extremely valuable, and I think more interaction, more collaboration between communities is a good thing, and I think we've still got a good way to go and in doing that. There's been collaborations, of course, in the past to develop many of the important a lot of the important work that's got us this far, but I think that there's still a lot of things to do. And from my perspective, I think just building off of that really is we have the opportunity to I think now get much richer data. I still thinking about observing someone for a few seconds and attempting to make an assessment of their feelings is such a limited view of what you could possibly do in this space. And so my particular bias is to look at longitudinal measurement to try to understand is there more we can learn about how about people's overall well-being, and how we can design technology to support people to help reduce stress or improve overall quality of life. And that data is going to reveal, I'm sure, many new things that we didn't know before. And as Alan described, like collecting that data in such a way that it can answer the right questions from a psychology perspective, I think will be very valuable, not just being limited by what we can do technologically, but thinking about what are the right questions to ask, and how can we design those experiments both to get the richest insights, but also in ways that are very sensitive to all of the big kind of ethical questions that I think we face also as a field. So yeah, to me there's a lot of exciting opportunities, and really I'd love to see more of that type of work in coming into these conferences, is going beyond just trying to beat benchmarks on existing data sets, but thinking about how we can really bring in expertise from psychology to inform the types of computer science approaches to sensing and measurement.
Jujun, do you go first? Or
I actually don't have much to add, so yeah, go ahead.
Okay, I'll go next then. So I think that we have to take a step back. I think I understand the question. We've talked a lot about data sets and sorry about the methods. I think I want to take a step back and say that the important question is not the data set or the methods, but actually the scientific question that we want to answer. A data set is only as good as and the methods, by the way, right? The data set and the methods are only as good as what they can answer, what they can address, what scientific questions they can illuminate or give some light on. So I'm going to give the example because, again, let me take a step back. People usually downgrade the role of data sets. It's only been until very recent years that CVPR and conferences like this are actually taking this very seriously. But in the biological sciences, that has been the case for many, many, many years. So for example, one of the most famous and important scientific breakthroughs of the 21st century has been the completion of the human genome. And that's just a data set. That's what it is. There's nothing else. But it's a data set that's created to answer a certain number of very fundamental and important scientific questions. And I think that not only the data set, but then the methods that were developed to mine that data set were developed to answer those questions. And that's what we need to do as a community. And then the second thing I wanted to address that I think Daniel has alluded to already is the ethics of what we're trying to do. So I'm going to disagree with Alan when he said that we could collect data on couples, for example, and then see whether, long-term they're going to get married or they're going to survive marriage over the long haul. I want to caution people to address questions like that or questions.
I don't mean do it without their consent.
Okay, but because this has been done, for example, in hiring people, right? And I think that we can do more harm than good in those occasions, right? We don't want to tell people you have to fit into that mold to be successful. Everyone's successful in different ways. So I think that the ethics of AI in general, but specifically here of affective computing, are very important, and they have been pretty overlooked to that point. So I like to see more of that as well.
100%. I just want to comment, because you mentioned ethics, that I am forming a nonprofit that is putting together ethical guidelines for the scientific inquiry side of things and building AI according to use cases that are approved ethically. So I'm totally on board with that. And in terms of the data, I think everything should be collected with consent, with people's full informed consent of what the data is going to be used for and what you can extract from it. And that's something that to some extent is covered in current privacy laws, like GDPR. And so compliance with those laws often gets you there, but it needs to go even further when it comes to affect, because often you don't know what can be extracted from the data set.
Well, I wanted to, it looks like we're about 11 minutes over, but I wanted to thank all of you for your amazing talks and also for the diverse perspectives you brought to the state of affective understanding research today. It was an amazing experience to hear all of this. And yeah, thanks again.
Well, thanks so for having us. And
yeah, thank you.
Looking forward to more discussion.
And for everyone else, our next event will be at 7 p.m. Eastern Standard Time, and that will be the talks going over the competition. See you then.
See you.
Hello, everyone. My name is Jennifer, a PhD student from Caltech. I'll be introducing the last session of our workshop on affective understanding in video. This session will be 2 hours long, where for the first half, we'll be going over some of the challenge talks from the top teams from the evoked expressions from Videos Challenge. And for the last hour, we'll have a live discussion panel. The motivation of our EEV dataset and challenge is that we want to better understand how viewers react to videos. So given this cat video, we want to understand how a general audience might react when watching this video. There are several different affective signals that have been studied previously. For example, some work studied how viewer self-report varies across time while people are watching videos. Other studies take physiological measurements, such as heart rates, while people are watching videos. Another way of studying this is to use facial expression reactions, which is what we use in our data set. So here, our EEV labels are based on facial expression reactions from reaction videos. For those who may not be familiar with reaction videos, these are videos that contain a viewer who's watching a content video where they're recording their facial expressions, and they have the content video overlaid on top of the reaction video. In the first step of our work, we mine reaction videos online by keyword, and we find the corresponding content video online from the reaction video description. In the next step, we use an expression recognition model to annotate facial expressions in the reaction video. And in this step, we mask out the content video overlay to prevent the model from using the content video in the recognized expressions. In the next step, we match our reactions to content video frames using the content video overlay, since there is an identical frame that the person is reacting to in the content video. And we do this matching step using SIP features. Finally, we combine the facial expressions that's been annotated from the reaction video with the content video frames. And the EEV dataset consists of a set of over 20,000 content videos that's been annotated with evoked expressions from the expression recognition model at each timestamp. Here, we release a subset of the EEV challenge from the dataset, and we see that our release dataset subset has around 5,000 videos with over 8 million frames. This is recorded at 6 Hz. The task here is that given the video content, as you can see, for example, this cat video, we want to train models that can predict expressions that's evoked by the video content from the reaction videos, without these models having access to the reaction videos. During evaluation, we take each expression in each video and we compute correlation. So here you can see we use this formula to compute correlation, where X would be the ground truth expression that's in each frame, and Y would be the predicted expression from the model. And we compute correlation over all videos and expressions and average everything into one value for our final leaderboard. One thing to note is that since our dataset consists of video links, if the video links are made private or unavailable, then we don't use those videos in our evaluation. So our challenge evaluation uses all the available test videos on April 24th, which was the last day of the challenge. When we look at our challenge stats, we see that we had 51 participants with 11 teams on the final leaderboard, with around 341 submissions. So when we look at this distribution, we see that there are people from many different countries. In particular, you can see here that US, China, Korea, and India are highlighted. You can still visit our challenge page and use our challenge evaluator to compare your models with the leaderboard. So here we see the top teams on the leaderboard are these 4 teams, which have been invited to give talks at our workshop for the next 45 minutes. And in particular, we would like to congratulate Team SML for placing first on the leaderboard. Finally, you can again download the subset of our data that was using the challenge. using this QR code on the left. And if you would like to evaluate your models against the leaderboard, you can still visit our challenge page using this QR code on the right. If you have any questions, feel free to contact us at this email below. And thank you for attending our workshop.
Hello everyone, my name is Huỳnh Văn Thông from Chennai National University, South Korea. And today I would like to present our solution for EV 2021 challenge with the title Temporal Convolution Network with Positional Encoding for Evoked Regression Estimation. So as you know, the Evoked Regression from Video Challenge 2021 have the video annotated as seed head with 15 continuous expression in range from 0 to 1. So it means for each second we have 6 timestamp, and for each timestamp we will have 15 continuous expression. And in the training we have around 3,000 video, and for validation we have around 700. And for the testing we have 1,300. And for the testing we do not have the label, and we need to submit to the organizer to evaluate the score. And the video is come from YouTube with different kind of clips, from music to the video to the entertainment to the news, and we need to read the score for each timestamp here. And the video have different lengths, from maybe from 80 seconds to 120 seconds or more. So our solution have two parts. The first is the feature extractor, and the second is the estimation module, which include the temporal and the regression. So for the feature extractor, we consider the two kind of information, the visual and the audio information. For the visual information, we read from its set head and resize it to the size of 224 by 224 to deal with the retrain model. And the retrain model will produce a vector with 1,280 dimensions for each frame. And for the audio, we resemble the audio to the 16 kilohertz, and after that we split it to the segment, and each segment we have the length of 1 divided by 6 seconds. From each segment, we will compute the log mass spectrogram with the size of 96 by 64, and after that we use regression models to extract the feature vector with the 2048 dimension here. And in the estimation module, we have the temporal and the regression module. For the temporal module, we build it based on the TCN residual block, the temporal conversion residual block. It consists of the related causal convolution and normalizer, such as the white norm, the rub out, and one by one convolution is used to ensure the length of the input to make the addition connection with the output here, similar to residual connection. So we will stack up the multi-TCN residual block to make our temporal module. And for the positional encoding, we encode the positional of the timestamp in the input sequence. So as you know, the training and validation set, the video have some missing, some video, almost the video will have the missing in the annotation for some timestamp in the video. It make the discontinuous in the label. So we use the positional encoding to let the temporal module know the different in time of the of each time of each uh, time point in the input sequence. So in the recent module, we use two fully connected layer with the row in the middle, and we will show the parameter of the module in the next slide. So for the feature extractor, we use the project model on the TensorFlow Hub, and you can find the project model in the footnote here. And for the temporal and regression module, we use the PyTorch 1.8, and we train our network with 20 epoch on the training video, and we validate with on the validation set. We train with the HGD optimizer with the learning rate of 0.005 with the bus size of 32, and we use the objective function in the mean square error. So you can see here the NB here is the bus size. It means 32, and G here in our training progress, we use we fit the whole video at a time to the network. So the bus size 32 it also mean 32 video during the training, and so the Z here indicate the index, the video index of the bus size, and the NC here is a number of class. So in the EV 2021 we have the 15, so NC will equal to 15. And the Y here is the ground vector, and the Y hat here is the radiation vector, and the NGL here is the number of frame in the video Z. So here is our parameter for the temporal module and regression module. So we also try the for the virtual feature. We use 3 blocks of the descent residual. For each block, each will have the 512 filter on the channel with the duration from 1 through and 4. And for the audio, we use 6 block of descent. So each block also have the 512 filter, and the duration is change from 1 to 4 and 1 to 4 again. For the header unit, we use 15 header unit for each fully connected layer is corresponding to the number of class in the task. So for the kernel size, we use the same kernel size for both visual and audio is equal to 3. And in the evaluation metric, the EV 2021 use the Gaussian correlation coefficient to evaluate the submission. So the Gaussian correlation coefficient is range from -1 to 1, with the 1 indicate the perfect correlation, and for the -1 indicate the imperfect correlation. So you can see here in the table our result on the visual and audio. For the visual, we use the efficient net B0 with the rough out is 0.3 in the temporal module, and the motional encoding which include. So we get the published and private score is similar, it's around 0.03. And for the audio, we have the 4 variant here. So let's see in the first two round here. They have similar with the drop out 0.3, but in here we have the first include the positional encoding, and the second it does include the positional encoding, and you can see the huge drop in the performance here. With the personal encoding, we have the score with around 0.05 on both the published and private text, but on the model which did not include the personal encoding, it dropped to the negative value in the minus 0.07 here. It indicate the importance of the personal encoding in the network. So, and we are in the last in the in the near the due date, the deadline, we submit two different version of the audio with the dropout 0.2 and 0.0 here. So we did not expect that the improve on the result, but it showed that with the dropout 0.2, we get the best result on the published and the private test for the single model here. And the audio model with the dropout 0.2 also get the best score over on submission. And we also make an example of the audio and virtual model. So the example here is the weighted average of the virtual model. Here the efficiency be 0 here, and the first audio model here. The mobileness was improved with the dropout 0.3 with the personal encoding. In here we indicate the audio. We have the last way is around 0.8, and for the virtual it is 0.2, and we take the average of the reason. So it make a huge improvement in here on the both published and private test. So as a summary, we present our approach for EV 2021 challenge with beyond the design and personal encoding, and our approach achieved the first place on a private leaderboard. Our support will be publicly available at the GitHub link here, the VR code here at the later day. And for the future work, we will consider the temporal information for the virtual data in each timestamp to try improve the result. And we also will try to learn directly the interaction between the audio and virtual during training instead of the live fusion, as you can see in the previous slide. That's all. Thank you. And we are waiting for the question from you. Thank you.
Hello everyone. Here we present our paper for the runner-up place in the 2021 Evoked Emotion Challenge. This talk is divided into the following 4 parts: introduction, our approach at the challenge, experiments, and conclusion. Videos, as rich media content, are capable of evoking a range of emotions of viewers. With the booming of streaming platforms, creating attractive videos has become a key demand for both platforms and creators. In the 2021 Evoked Expression from Videos Challenge, we are required to generate 6 Hz predictions of 15 emotions from the given videos. This closely resembles the emotional impact of movies task in the medieval competition. Both requires the participants to predict the expected emotion of the general population with respect to a given video. This kind of dense labeling of the frames also reminds us of the task of action segmentation. Similarly, in action segmentation, we are required to distinguish the action type of each frame. The difference is that in action segmentation, we take the category with the maximum output. In EEV, we focus more on the different levels of each emotion and take the logits as the output of frames. When constructing the model for the EEV task, we could also use methods from action segmentation to perform the temporal modeling step. The best performing model in medieval task utilizes recurrent neural networks to model the temporal relation between frames. Temporal convolutional networks is also proved to be performant and more efficient compared to RNN in the action segmentation task. Like multistage TCN, it outperforms GRU and bidirectional LSTM on action segmentation task by a significant margin. In our submission, we follow the former approach and use bidirectional GRU to model the temporal relation between frames in our model. Here we explain our model in detail. We follow the model proposed by Sun in the EEV dataset paper. We also extract the visual and audio features from the original videos. For visual features, we deployed off-the-shelf swing transformer Swing L, which result in 1,536 dimensional features for each frame. For audio features, we use VGG-ish pre-trained on YouTube 100 million. The audio track of each video is first transcoded into 16 kHz mono audio and then using the method from AudioSet to compute the log mel spectrogram. The 19.4 by 64 log mel spectrogram is then fed into VGG-ish, resulting in an audio representation of 128 dimensions. The pre-computed features of each modality are fed into two-layer bidirectional gated recurrent units without sharing weights. The bidirectional GRU builds the correlation in the temporal space. Comparing to unidirectional GRU, it takes both the past and future information into account, which enables us to form a better generalization at each time step for each modality. Each of our GRU modules operate for 60 time steps. When we sample the input video at 1 Hz, this will give us a temporal perception range of 60 seconds. To fuse information extracted from different modalities, we adopt the late fusion strategy. The output of GRU is concatenated as the video representation. Context scaling is used to exploit the dependencies within the fused feature vector. In the end, another context scaling layer is added along with a sigmoid activation layer to calculate the final prediction. As for loss, we settled on a simple L1 loss. There will be more discussion on loss in the following slides. During the challenge, we conducted our experiments based on two key observations of the label data. First, the labels are noisy and contain sudden changes to 0. Second, the summation of the 15 emotions are not supposed to be 1. Each emotion is independent and range from 0 to 1. One successful experiment is linear interpolation. We train our model on 60-frame video clips with 1 Hz sample rate, which covers a 60 seconds time span. We consider 3 different strategies to obtain the dense prediction and 6 Hz for submission. First, we consider to keep the input frame numbers to 60 frames and change the sampling rate from 1 Hz to 6 Hz. The time span is also reduced from 60 seconds to 10 seconds, which compromises the inference results. Second, we keep the perception range at 60 seconds and sample the frames at 6 Hz, resulting in the input of 360 frames. In experiments, we find that the dense inputs harm the performance. Third, we can use the linear interpolation strategy to upsample the 1 Hz prediction to 6 Hz. Each emotion is upsampled separately. The results of 3 different strategies can be seen in the right table. It's clear that the last strategy with linear interpolation performs best on the validation set. For the final submission, we also adopt the third strategy and find that the sparse input sampling and the dense prediction interpolation are helpful. Here we report one failed attempt. From our observation of the expression labels, we find that it contains high-frequency noises and sudden changes to 0. These factors make the data hard to fit. Therefore, one straightforward idea is to use low-pass filters to filter out these high-frequency noises and ease out the sudden ramps. One example of Butterworth filter can be seen in the above image. Left and right image demonstrates two different filter configs separately. The left one removes more high-frequency components than the right one. This results in a more smooth filtered label, but also loses more information. To test this idea, we calculate Pearson's correlation coefficient between the filtered label and the original label in the second column of the table. In practice, we choose filter configurations that result in the highest correlation with the original data. When we train the model to fit the filtered label, this label correlation score can be considered as an upper bound of the model trained on the filtered data. While the smoothed labels are easier to fit, we observe that the model learned on filtered labels do not achieve better performance than the model learned on the original data. As the loss experiment is about different loss functions, in our model, we use a simple but yet effective L1 loss. One optional method is to use the KL divergence loss to minimize the distance between the predicted logit and the ground truth label. But as stated in the EEV dataset paper, each label is consisted of 15 independent emotion values ranging from 0 to 1. They do not sum up to 1 for each frame and certainly cannot be considered as a distribution. However, testing after the challenge reveals some interesting results as shown in the right table. The KL divergence loss outperforms L1 loss we use in our final submission on the validation set. We also tried another alternative correlation-based loss called concordance correlation coefficient, which can be seen in the left equation. Existing work has shown that concordance correlation coefficient performs better than error-based losses in terms of average concordance correlation score. Mu x and mu y are the means of the two variables, and sigma x squared and sigma y squared are the corresponding variances. Rho is Pearson's correlation coefficient between the two variables. This eliminates the square root part in Pearson's correlation and makes it easier to optimize. In our practice, although concordance correlation is more stable than L1 loss on the training set, it leads to a worse correlation score on the validation set. In this presentation, we present our approach for the viewer reaction prediction. Our model takes the advantages of both image and audio modalities to build the temporal correlation. During inference, we use the linear interpolation to generate dense predictions from sparse predictions. Albeit simple, the proposed method has achieved the second place in the EEV Challenge leaderboard. In the experiment, we not only illustrate our detailed solution but provide our field study on different loss terms and label smoothing strategies. We hope it can pave the way for future works on reducing the noise in the labels or a new loss function to regularize the model training. In the future, we will continue to study more discriminative cross-modality losses, such as instance loss and clip loss. This is the end of our presentation. Thanks for your attention.
Hello everyone, my name is Baoming Yan from Alibaba Group. Today, I will briefly introduce our technical solution of the recent invoked expression from videos challenge. The title of our method is Multi-Granularity Network with Model Attention for Dense Affective Understanding. Affective understanding is a task that aims to predict the viewer's expression invoked by the videos, which could be applied to video creation and recommendation. In the recent EEV challenge, A dense affective understanding task is proposed and requires frame-level affective prediction. As shown in this table, there are almost 5,000 videos corresponding to 3,370 hours are provided. 8 million frames are annotated with 15 viewer expressions. Each expression ranges from 0 to 1 in each frame, corresponding to the confidence that the expression is presented. The expression of each frame in the test set is required to predict, and the evaluation score is the average correlation of each expression across the video frames. For this dense prediction task, we consider that the expression of the specific frame could be determined by the signals of various time scales, and we should employ multi-granularity features for better description of the target frame. Hence, we extract the multi-granularity features for each video. The multi-granularity features could be divided into 3 levels. It's a frame level feature, clips level feature, and video level feature. This multi-granularity and multimodal feature then fed into the model attention fusion model to fuse the various features into a global feature. Then we use a MOE mixture of experts classifier for expression prediction. This is a detailed description of the multi-granularity features. The frame level feature contains image features and audio features. For image features, we use Inception ResNet v2 pre-trained on ImageNet to extract this feature. This feature may contain visual silent content of the frames. Audio feature is extracted by VGG style model provided by audio set on preliminary vision of YouTube ATM. The audio style information could be extracted. And the clips level feature represents semantic context information around the frame. For example, human behaviors, semantic information from speech. S3D CNN backbone is used to extract features for human behaviors. The S3D backbone is trained by self-supervised information between visual content and speech text on how to 100M dataset. We also download the subtitles of the videos and find the nearest speech text for each frame. Then a pre-trained BERT model is used to extract the feature. The video level feature consists of the main affective information related to the theme of the video. We train a video level expression prediction network on the EEV dataset. The video level expression is obtained by the averaged labels of frames. The output of the last hidden layer of the model is used. The model attention fusion model is proposed to emphasize more affection-relevant features. We first contented the above multi-granularity multimodal features and predict the weight of each feature. Then the weights are used to emphasize more relevant features. And some features may be missing in the video. We use model level dropout to make the model robust. A 3-experts MOE model is used for expression classification, and we use BCE loss to train all the parameters in our model. This is the experiment part. To evaluate the importance of different granularity of features, we start with frame level features and gradually add the clip level features and video level features. The experiment results on test set of the EEV dataset are shown in this the left table. For the frame level feature, the performance of image feature and audio feature is evaluated separately. We could see that audio is more effective than visual content for affective and prediction. And the combination of image and audio feature could further increase the performance. And after the introduction of clip level features, the correlation score is remarkably improved. This indicates the importance of thematic context information around the frame. It is noted that the subtitle features are more effective than spatial temporal features. This means more thematic information exists in the subtitles. And the introduction of video level features further increased the performance and prove that the importance of the affective information from the whole video. We further evaluate the performance of model fusion and the classification model. MOE is more effective than MLP, and our model attention fusion is more effective than the concatenate operation. We use ensemble methods to achieve better results. For the dense affective understanding task, our method has two contributions. The first is multi-granularity feature construction. The model could learn more thematic context and video theme information. The second is model attention fusion, and the model could emphasize more affection-relevant features. That's all. Thank you.
Hello everyone, we are the visual analysis of humans team, which belongs to Open Research Institute. Our members include Quan Sun, Chen Chen, Xin Qiangtao, Yan Dongguo, and me, I'm Chen Zhang. Since the amount of all annotations is too large, we sampled 200,000 samples from the original date at training set. We set the sampling interval to 18 and set threshold by category to skip the cases where all kinds of expressions scores are below the threshold. As recorded in the table below, taking the training set as an example, we got about 200,000 time steps with expression scores. Considering that the expressions invoked by the video at the certain moment is only related to the video contact before. For each time step, we start with a keyframe and collect 6 seconds clips along the opposite direction of the time axis at the video date. For audio processing, we use a two-dimensional convolution neural network to extract features and regress expression scores after converting the original audio signal into a male spectrum. Considering that the audios in the dataset are not limited to human voice, we use male filter bank with a same bank head, which can retain more high-frequency information than the male filter bank with same bank area. For visual, we realized our network structure by replacing the classification head of CSN with a regressing head. CSN is certainly one of the state-of-the-art for action regression using 3D convolution. For audio, we realized our network structure by replacing the classification head of ResNet for audio with a regression head. The main difference between ResNet for audio and ResNet is that in order to maintain the resolution of the time dimension in the time frequency information of the audio, the several shallowest convolutions of the ResNet for audio are only performed in the frequency dimension. In the initial experiment, we set the loss function as L1 loss combined with L2 loss. However, we found that such a loss function only regressed the expression scores corresponding to each video clip, and didn't restrict the association between the video clips. Therefore, in our subsequent expressions on audio, we directly introduced the Pearson correlation coefficient as a penalty in the with loss function, and for each batch, calculating 15 expressions categories. Our example strategy for the regression result of video and audio models is to sum the values after be multiplying by the weight. The weights are proportional to the Pearson correlation coefficient, a metric of the single model. The table is part of our experimental records, and the Pearson metric is calculated on the subset of the validation set we sampled. Due to the lack of time, we did not conduct an enhancement experiment of the loss function on the video, but on the audio, we can say that the additional penalty we introduced for the loss function can improve the performance of the model. In addition, the offline example strategy is also effective. Thanks.
Oh, well, first of all, thanks everyone for the great talks. And thanks for joining us on the panel for the top participants of the EV Challenge. To get started, we first want to share a recording with attendees who might not have made it this time, but would like to watch our discussions after. Does anyone on the panel have an objection to this? If so, feel free to unmute and let me know, or you can send me a chat message on Zoom. Okay, I guess I don't see any objections. So Gotham, did you want to start recording?
Yeah, I'll start right now.
Okay, thanks. And also, can everyone on the panel from the top 4 teams please please show your video if you are able to, so that we see who the panelists are. Great,
Yeah,
I see people showing up. I'll just wait a little bit. I mean, I guess the talks was over a little earlier, so I thought we start first. But we can also wait a bit if the panelists aren't around at this time. But if you are here, please show your video so that we know you're here. Thanks. Great. I guess we are waiting on 2 more people. Or just 1 more person, I think. Let's wait until for 3 more minutes until 50 minutes, and then we'll start. Oh, actually, I think everyone's here. Okay, let's just get started then. So I'll first introduce myself. So I'm Jennifer, one of the organizers for the Affective Understanding video workshop. And we just, of course, want to congratulate your 4 teams for being on the top of the EV Challenge leaderboard. So for this panel, we're going to be going through some prepared questions, as well as questions from the audience. And if you're in the audience to ask a question, you can raise your hand in a Zoom call or use a chat feature on Zoom or a Google form. So for the first part, let's have all the panelists introduce themselves. So what's your name, what your affiliation is, and maybe say a few sentences about like your model, just to give a recap for everyone else. Let's start with the first place team.
Yes, so hello everyone. My name is Van Thong Huân from John National University, South Korea. So our solution with the title by on the temporal proportional neural network and personal encoding. So our solution achieved the first place on the EV private with the board. So our model have two main parts. The first is the feature extraction. It's based on the retrain model on the ImageNet and the audio set. And the second part is the temporal module. Is based on the temporal convolutional network. And we also add one more dimensional to the feature, that is the personal information. That to let the model know how much the difference between two task time in the input sequence. As we may know in the EV training and validation set, we have some task time that do not have the annotation that we ignore during the training. So it will make the input sequence discontinuous. So that's the one key point that help us to achieve the better score on the private test. That's all. Thank you.
Yeah, thank you. Let's go to the runner-up team. Is a team for less is more here?
Oh, yes, we're here.
Oh, okay, cool, thanks.
Oh, okay. I'm Ko Zhou from Zhejiang University, and I'm an undergraduate. And our method primarily involves training a RNA-based model on 1 Hz sampling of the videos and use linear interpolation to generate the final 6 Hz predictions.
Okay, thank you. Let's go to the multi-granularity network team.
Hello everyone, my name is Bao from Alibaba Group, and I'm a agronom engineer. And my solution is the multi-granularity network with model attention in dense affective understanding. Yes.
Thank you. Let's go to the 3D CNN to predict evoked expressions from videos team.
Hello everyone, I'm Chen Zhang from Oppo Research Institute. Thank you.
Okay, thanks for your introductions. So actually, for the first question is actually for all the teams. So if you have any thoughts, just unmute and jump in. So the first question that we got was, what are some challenges that you had while developing your solution? And in particular, was there anything that you tried that was sort of unexpected as you were working through your solutions? Would any team like to start? Okay, if I'm getting no volunteers, I'm just gonna go in opposite order. So let's start from this 3D CNN team. Chen Zhang, I think. Do you need me to repeat the question? Let me know if you're having technical difficulties also, and I'm happy to move on to someone else. Oh, okay. I guess like I'll first repeat the question and then maybe let's start from a third place team. So the question was, what are some challenges that you had while developing your solution? And was there anything that was unexpected? And let's just start from the third place team, the multi-granularity network team. Oh yeah, thanks.
Just could you please repeat the question?
Yeah, so the question was, what are some challenges that you had while developing your solution? Like, so what was something that was difficult when you were creating your model?
Okay.
Mhm.
I think as the dataset is predicted by a trained model from the face picture of the face of the viewers. I think hence the label is very noisy and it is easy to overfit the dataset, and the model will be can't be general while in the test set. I think it's the most difficult for us to train the model.
Thanks.
That's all. Mm.
Yeah, thank you. Did the second place team want to have anything to add on your solution?
Yes, we also experienced some instability during the training process. Our model did not converge to the same point during different training sessions. And another thing is that, as we have stated in our reports, we use L1 loss, but in our tests after the challenge, we found out that KO divergence also works and results in a better validation correlation, but we cannot test it on the final test set.
Okay, thank you. And what about the first place team, the temporal convolutional networks team?
Yeah, actually, the most bad is for the future detector. That will take a lot of time for us to experiment on the first day that we start with the challenge. And for the second part is about the loss function. As the traditional method, as the traditional trend on the training network that we use the object function, the metric function, the loss function corresponding to the metric function to optimize the network. As here is the correlation score. But at the experiment, we can see that when we use the directly the matrix as the loss function, we can achieve the very good score on the training as well as the validation. But if you do opposite on the test set, that we may have the negative score. So that take out a lot of time to try to analyze how it does. But it is not success, so we back to the traditional loss, that is the mean square errors. That's all.
Okay, thank you. Okay, so there's actually like another question that's a bit on the other side, which is that was there anything you tried that seems the most promising? So like, is there any particular part of your model that you think helped a lot, like in you achieving your final good spot on the leaderboard? And let's start with the first place team on this one.
Yeah, actually, in our block, the keyboard is the personal inputting. So, as in the present, we can say that we set that in the dataset, the training and validation. We have some husband that did not have the annotation during the error in the annotation forest. As we can see in the dataset script on the GitHub, but for the test set, we need to reduce on the timestamp. So it had we need to consider how much the difference between two timestamp in the input sequence for training. As in the LSTM or the temporal model, the time the output of time t is depend on the output of time t minus one or time t minus two, and in here due to the discontinuous at the label, so the difference between two timestamp in the input sequence may be different, maybe two or three or one something. So we need to let the network know how much the difference to take care of this here and during the take care of it during the training and leverage on the test set to achieve the better result. That's
I
all.
see. Thank you. Does the less is more team have anything to add? I guess, like, so I can repeat the question. So the question was there anything that seemed the most promising in your model? Like any particular component you think that helped a lot in producing the correlation, like higher correlations values you had relative to the other entries on the leaderboard? And in the paper, less is more, sparse sampling for dense reaction predictions, did your team find anything that you want to comment on for this question?
I think the most important part is the linear interpolation part. It's almost doubled our performance, the correlation score on the final test set.
I see. Thank you. What about the third place team, the multi-granularity networks?
Okay, I think the most important part in our solution is the multi-granularity and the multimodal feature, as we do many works to find the most effective modal features. And we start with the visual features, and after we introduce audio feature and the subtitle features, and our performance is increased very large. Yes, that's all.
Thanks. What about the 3D CNN team?
We think the most promising part in our method is the loss function, because at the beginning we just directly use the loss function, the L1 loss and L2 loss, but the performance was not good. Then I added the Pearson coefficient as a penalty index. Then the performance of our model are becoming very good. So we think it is the very important part in our method.
Thank you. I think from this discussion, it's really interesting that different teams had different things that were very helpful. For example, adding different modalities or doing sampling or like different loss functions. I wonder if all the methods were combined, we could do even better on this data set. Okay, I guess there's another question, which is that what are some of the things that you think would work well for this task, but you just didn't get time to try? Because I know the challenge was like a few weeks. So like, what are some of the future directions you think might be interesting? Does anyone want to jump in on this question?
Yes. So, in my opinion, so one approach can achieve the better result that we directly framing the for approach to improve is we can directly frame the audio and visual model together at the same time. It's in the I say in the less is more the next in the less is more approach that and in the baseline that we frame the three kind of feature face the visual information and the audio at the same time. But in my approach that I did not try is due to some limited on the computational result. So we can try. We have another kind of rock that in currently we only use one timestamp or one frame in the time in the 1 divided by 6 timestamp second 1 divided by 6 second to use the virtual feature. But for the audio, that we use the whole segment, which include the temporal information. But currently we did not include it, so we may try with is we use the 5 frame at each timestamp to get the temporal like the mean standard deviation directly with the temporal module. Yes.
Yeah, it would be interesting to see like how the method can be further improved for sure. What about the second place team for less is more? Is there anything that you guys wish you had more time to test? That would be really interesting for future directions.
During the process, we noticed that the order of magnitude of each emotion is different. So we tried to do the score prediction in 2 steps. The first is for the whole video, we predict a base like an average score for each emotion. And then during the process, we just predict the variations. We had this idea, but we didn't finish it.
I actually like that idea a lot because, yeah, like in the data set, I did notice that as well. So I do think that, like, if say the expressions were really close to the average, then like your model just has to learn the residual instead of like where the average is. So like, I think that's a really interesting,
yes.
yeah, like thing to explore. Yeah, thank you. What about multi-granularity networks? Anything you wish you had time to do?
Yes. I think as our solution use the pre-trained features as in IBNet or in YouTube 100 million, I think if we could train the model end to end, maybe the performance could be improved. But the computation consuming is too large. And the second one is our model is easy to overfit to the training set, and if we can decrease the overfitting, maybe the performance could be further improved. That's all.
Yeah, thanks. I think one thing that could help with that is like a bigger data set too, because like this problem, like you guys all saw and like tried, is like really complex. And so I think for overfitting, if the training set was like very large, then that might help as well. Thanks for your thoughts. Okay, what about the 3D CNN team?
For our team, I think is the TCM model, because we didn't use the TCM model in our submission, but we want to try that model, but we didn't have more time. But we see other teams or use the TCM model and the performance is good. Yeah, so we will try that next time.
Yeah, I definitely agree. There's so many like architectures that like it's easy to run out of time on these challenges. But if you do get time to try it, you can still submit to our challenge page and then see how it looks because our challenge evaluator is still up. All right, I guess there's like a different sort of question for you guys. So like as you were working with the data set and like doing this expression prediction task, you know, the dense predictions on each frame, what do you think you might want to see in future iterations of the data set? Like what in the data set would make it more interesting to you or make the problem like say easier? And anyone feel free to jump in. Otherwise, I'm gonna call on people. Okay, I'm gonna start backwards. The 3D CNN team, do you have any comments on like what you would like to see in future iterations of the data set?
We don't have any suggestions. Sorry, we think the data now is is good.
Oh yeah, no problem. It was more like a longer term question, just to see your thoughts as participants and like users of it. But thank you. What about the multi-granularity networks team?
I think if the topic or the theme of the video is provided, then more information will be because then it will be much easier for the expression prediction.
Right, because if I recall, your team used a lot of different modalities, right, including subtitles. So like I guess, and in your experiments, I think adding each modality increase your correlation score. So like I guess you're saying you could use a theme as an additional like modality to increase the score even further. Yeah, that would be that would be interesting to see. Thanks. What about the less is more team?
I think it would be great if in the future iteration of the dataset, the noise of the labels maybe can be reduced. Like there is a lot of continuous zero labels in the training data, and I think that it's hard for the model to fit this kind of data. Thanks.
Yeah, that makes sense. I guess you guys sort of got around it by doing the subsampling. But if there was no noise in the training data in the first place, then like I suppose you wouldn't need to do a subsampling. Like that was why you introduced it, right?
Yes.
Okay. Yeah, that makes sense. Thank you. What about the first place team?
So as we can see on the evaluation for each kind of expression, we can see that some expression have the high score and some expression in the other hand it have the negative score. So you can see that the data set have a very imbalance on the label. So currently we judge the average on the score with the equal weighting. So how about in the future if we organize the challenge that we weighted average that, so we have consider more on uh, the 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 minor class that have the negative score, so we can balance on the score like we have on the F1 scores for the classification. And in here for the correlation, we downweight of the major class and the upweight of the minor class, so the score will much meaningful.
Thank you. I guess like thanks to also everybody for the suggestions. Like we'll definitely take that into account and think about how like we can better improve our data set in the future as well. So there is a question specifically for the first place team. So like I guess actually we talked about this in the poster session this morning, but since everyone is here right now, can you comment on why the positional encoding it's so important in your model architecture, and maybe explain that a little more?
Yes, actually, in the let's not we said that in the dataset we have some parameters that have all now annotation that we have the zero score for all of the emotion. So we ignore the kind of timestamp. So the input sequence, the how video will have some we will discontinuous. We will be discontinuous. So for example, we have the timestamp 1, 2, 3, and we will have 4 and 5 timestamp 4, 5, 6 have a zero score for on emotion. So we ignore 4, 5, and 6, and we add the 7, 8, 10, 8, 9, 10, something like that. And we can see the difference between two timestamp is 1, 1, 1, and is 1, 2, 3, and it will reduce to again 1, 1, 1. So that will be the abnormal on the for you with the LSTM or the PCN that we can say is in is defined is the define of LSTM that the output of time t it depend on output of time t minus 1, t minus 2, or t minus 3. And in here, for example, at the time A, we only have the time 1, 2, and 3, and we do the 1, 2, and 3, and 4, 3, and we do not have the 5, 6, 4, 5, 6, and 7. So it much gap here. So I think that is the reason that the LSTM or the temporal model will did not take care of this. But for the on the test set, that on the we need to take into account on the timestamp. So it's one reason. And in here we use the positional encoding. It's just a symbol that we fit onto the network the timestamp. For example, in here we have the 1 divided by 6 and 2 divided by 6 or 3 divided by 6 to the sequence. And the network will know the current timestamp, the current timestamp and the next timestamp how much is the difference. So it will take care of this, and it will also bring that to the test set and go to the result.
Yeah, thank you for the explanation. There's a question for the less is more team as well. So here, like the sparse sampling strategy used is like really interesting. Do you think like adaptively sampling with different frame gaps could work even better? And could you comment a bit more on the other sampling strategies that you've tried? The less is more second place team. Should I repeat the question?
There's no need to repeat the question. I'm just
Okay,
wondering,
sure.
the adaptive process you mean, can you maybe explain more about the adaptive process you mean in your question?
Yeah, so I think what it means is that, like, I think that in your paper you mentioned you were evenly sampling, like,
yes.
Yeah, but I guess it's possible to choose frames that maybe the model is more confident with, or frames that you think there's less noise, and then choose different gaps for sampling. Do you think a strategy like that might help in this data set? And what were some of the other sampling strategies that you might have thought of?
I think it might help. The sparse sampling mainly deal with the noise neighbors in the in the training data. Like if there's a continuous zeros in the data. If we do the adaptive process, I don't think our model can judge whether the data is usable from the video itself, because we don't have the relative informations.
What were some of the other sampling strategies that you tried? Like, I think you mentioned some in your paper, but maybe like you could talk about it for a bit so that everyone can hear about them.
So in our paper, we used 1 Hz sampling. Another method we didn't mention in the paper is that we can use 1 Hz sampling, but we use an offset. As for now, we just sample the start frame of the 6 frames. If we use offset like 0, 1, 2, 3, 4, 5, then we merge the results. That's equivalent to dense sampling, but just we do it 6 times. So we got the final 6 Hz.
I see, but that didn't work as well as the 1 Hz one, right? I'm guessing.
As a matter of fact, we didn't have enough time to try this method either.
Yeah, it would be really interesting to see that. But of course, if the data set had like less noise, then like, I guess you wouldn't need, I guess your hypothesis is that you wouldn't need to do the sampling anymore. I see.
I think another assumption is that the change with the emotion is not that intense, so we can do the lower sampling rate.
I see, that makes sense. Yeah, thanks. Okay, so I guess the next question is for the multi-granularity networks team. Okay, so this question is that, like in your model, you considered a lot of different modalities and temporal windows, and that was really interesting. Like your subtitle features also used like BERT, I think, which is pretty cool. Do you think one direction for future work in this area is to add like more modalities and like, you know, use other maybe pre-trained models? Or like, do you think video and audio should be able to do this task?
Could you repeat the last question?
Yeah, no, of course. So in your paper, you investigated a lot of different modalities. Like, so a lot of the teams looked at, say, just video and audio, but your team also looked at, you know, subtitles and actions. And that was pretty interesting. So do you think one direction of future work in this like expression prediction area is to like look at a lot more different modalities and add those information into training the model? Or do you think, you know, maybe video and audio is the way to go based on your experiments?
Okay. I think for expression prediction, more model feature could be helpful, and how to find the most effective and the most correlated feature is very important for us to establish the relationship between the video content and the viewer's expression. I think maybe it's promising. Yes, and only the visual and audio feature is not enough to predict the expression of the viewer, and more models is needed. Yeah, that's all.
I guess a follow-up question is, how did you choose like subtitle and action like modalities? Like, how did you know what to add?
first, we we download we view these different models from the training dataset and find first for the subtitles it may be some semantic information from the subtitles as we think is maybe useful, so we add it to the model and find it could improve our performance. And for the human behavior or temporal feature, and this is the experience from our other project. Is very helpful. Yes.
Okay, thank you. And well, so this question is going to be for the 3D CNN team. And for this question, I guess in your talk you mentioned that you did sampling and some thresholding in the beginning before you trained the model. How did you choose like that sampling stage and the thresholds?
Yeah, we just try a lot of different thresholds, and yeah, it's a little bit empirical. Yeah.
I see. And was your model trained from scratch? Like you didn't use any pre-trained models, right?
We just use for our visual model, we use a pre-trained model for CSN. It's released from Facebook. I think it's a very, yeah.
Oh, but for your audio model, did you also use a pre-trained model?
We didn't use pre-trained model on our model pathway. Yeah.
I see. So just for video.
Yeah, just
was
video.
that? I see. Okay, thank you. Okay, I guess I am actually gonna loop back to the first place team again. Because there's one question here that says, like in your paper, you mentioned that you would like to investigate the interaction between video and audio modalities. Could you expand more on like the types of interaction that you would expect to like explore?
Yeah, actually, in that kind of interaction, we have two approach. The first is we train an end-to-end network, and we did not use the return feature or something, but we can train from scratch. We use a return way, and we need to fine tune. And the second is we use a loss function, the weighted loss function, the learnable loss function to adjust uh, the way of the virtual and the audio the virtual and the audio uh, architecture. So this means beside the final loss that we have the separate loss, for example, loss for the audio, loss for the video, and the total loss that is the weighted average with the learnable way, with a learnable way. So first of all, the alpha and beta is depend on uh, the the way depend on the outputs of the network. We can use some kind of attention of the network, and we can in the end-to-end. So the alpha and beta will change, and we will have the direct interaction between two other. That is the last output. We also can have the middle output. So instead of give the output of the temporal module, the last FC layer followed by the temporal module, we can view directly the output of the spatial information. I mean the output of the visual and audio, and we directly add a fully connected layer and output the score, and we will have maybe a total of 4 or 5 loss, and we average all of them with the learnable point. That's
I
my
see.
talk.
Thank you. Okay, so I guess moving on to the second place team for less is more, you actually mentioned a few directions of future work in your paper as well. So like you talked about some losses and tasks you would like to explore with your model. Could you comment a bit more on what you think like your future works might look like? I guess I can give a bit more context if you'd like. So like, I guess in your paper, let me just open it really quick. I think you mentioned that there are like different loss functions and other tasks that are related to this. Actually, you mentioned that in your video as well, I think, where you said related works are like action recognition or like other types of video understanding tasks. Like, so do you see that your future direction would be applying these models to like other video understanding tasks as well? Like, do you think your same model can be trained for other video understanding tasks? For the second place team?
Yes, I think it might be applicable. Like in tasks like I think in the paper we mentioned about sign language recognition. So the same model might also be used on that to do like frame level annotations of the video about what words it's speaking in a specific frame.
Right, I guess, so just to confirm my understanding as well, so in general, you're saying that your model could be applied to any, or I guess some video understanding tasks where the output labels are continuous. Like since you're training in a supervised way, you would just replace the training data then with say data from sign language recognition. Is that what you're saying?
Kind of, but I don't imply that it can be applied to every task like that. I just say that we can try this model on the task.
Yeah, it would be really interesting to see where that goes. Thank you for the clarification too.
Yes.
Yeah, so for the multi-granularity network team, I guess like I think you had frame, clip, and video level like granularities for your features. Was there any particular one that you thought was more useful than the other ones, like during your experiments?
I think the most effective feature is the frame level, then the clip level, and the video level, and this is tested from the test set because for the we should predict the frame level of affection labels, and if the feature is in a large time scale, then the result will be smooth, then the correlation score will be lower. So the frame level is also in this way, the frame level is very important. But the clips level and video level provide a very good context for the precision for the good prediction result. That's all.
Thank you. That's all the questions that we got for the panel for now. So if anyone from the audience would like to ask any questions, like you can do so in the chat or you can raise your hand. And we'll wait like a couple of minutes to see if anyone asks questions. But otherwise, I guess we can sign off in 5 minutes or so if we don't get any questions. Thanks to everyone for participating on the panel. It was great learning from your approaches. Okay, I think it's been like a minute and I didn't see any questions. So I guess this is the last session of our workshop. So thanks everyone for coming and attending our workshop. And we'll make the recordings available so that you can watch it afterwards. If you have any more questions, just reach out to us through the contact information on our website. And for anyone in the audience, if you want to submit questions later, you can still use a QR code to do this. Thanks a lot again, everyone, and congrats on being on top of the leaderboard. Bye.
Bye. Thank you.
Bye.
Bye.